Something out there in space is so dense, so heavy, and so strange that it almost breaks the rules of physics. These are ultramassive white dwarfs, stars crushed down to sizes smaller than Earth but packing more mass than our Sun. They live on the edge of collapse, caught in a cosmic tug-of-war between gravity and the forces holding them up. What are these mysterious objects? How do they form? And what secrets could they unlock about the universe? Let's find out. You know how stars end. Big ones explode. Small ones fade. And the in-between stars? They become white dwarfs. These are the cores left behind after a star burns out, sort of like a burned log that's still glowing at the end of a campfire. White dwarfs are dense. Like really dense. Imagine a sun-sized star squashed down into something the size of Earth. That's a white dwarf. Normally, there's a limit to how massive a white dwarf can be. It's called the Chandrasekhar limit, and it's about 1.4 times the mass of our Sun. Anything heavier than that should collapse under its own weight and become a neutron star or a black hole. But here's the thing, we've found white dwarfs that are heavier than this limit. Way heavier. We're talking 1.5, 1.6, even close to 1.7 solar masses. And they're still just white dwarfs. They haven't collapsed. They're just out there, chilling in the cosmos, flipping the bird to gravity. And that should be impossible. So what's going on? First, let's break down what a white dwarf really is. It's the core of a star that's run out of fuel. When a star like our Sun gets old, it swells into a red giant, then sheds its outer layers in a glowing shell of gas called a planetary nebula. What's left behind is the white dwarf, just the core, no more fusion, no more pressure pushing out. The only thing keeping it from collapsing completely is something called electron degeneracy pressure. Basically, electrons don't like being squeezed into the same space, so they resist being packed too tightly. That resistance is what keeps the star from imploding. Now, electron degeneracy pressure has limits. Once you pass a certain mass, the Chandrasekhar limit, it's not enough. The star should collapse. That's the rule. But space doesn't care about our rules. The discovery of ultramassive white dwarfs throws a wrench into everything. Scientists found a white dwarf called CTFJ 1901+1458 that might be the most massive white dwarf ever seen. It's about 1.35 times the mass of the Sun, and it's only about 2,600 miles wide. That's smaller than Earth. Think about that. Something more massive than the Sun packed into something smaller than our planet. That's like stuffing an elephant into a suitcase and still having room for snacks. But CTFJ 1901+1458 isn't alone. It might be the most extreme, but it's not the only one. Astronomers are finding more and more of these ultramassive white dwarfs, and they're all raising the same questions. Are our models broken? Is there new physics we don't understand? Or, are these not ordinary white dwarfs at all? Some theories suggest that ultramassive white dwarfs might be the result of two smaller white dwarfs merging. Picture two dead stars in a tight orbit, spiraling into each other over billions of years until they finally crash together. The result? A heavier white dwarf. That sounds cool on paper, but there's a problem. When two white dwarfs collide, the result is usually an explosion, a type I supernova. These are some of the brightest events in the universe. But ultramassive white dwarfs like CTFJ 1901+1458 haven't exploded. They're intact. They exist. So maybe, just maybe, something we don't understand is holding them together. Could they have magnetic fields strong enough to help balance the pressure? Some researchers think so. Maybe insanely powerful magnetic fields, billions of times stronger than anything on Earth, are somehow giving these stars the extra support they need to stay intact. That might help explain how they can be so massive without collapsing. But it's still just a guess. The truth is, nobody knows for sure. And there's more. These ultramassive white dwarfs are fast. Some of them are spinning at ridiculous speeds, completing a full rotation in just minutes. That's faster than any normal white dwarf should spin. It's like they have a built-in motor that never slows down. The faster something spins, the more centrifugal force pushes outward, like water spraying from a spinning bottle. Maybe that outward push helps counter gravity too. It's possible. But again, that's just another piece of a puzzle we don't fully understand. Let's talk gravity. Gravity is what should be pulling these stars inward. At these masses, gravity should win. But it doesn't. So either something else is pushing back harder than we expect, or gravity itself isn't acting the way we think. That's a wild idea, but some physicists have actually proposed that gravity might behave differently under extreme conditions. Maybe the fabric of space itself gets weird at super high densities. Maybe there's a repulsive force we haven't discovered yet. Maybe there's something beyond Einstein's general relativity happening inside these stars. And that opens up a whole new set of questions. If ultramassive white dwarfs are stable, then maybe the Chandrasekhar limit isn't as solid as we thought. Maybe it's more like a guideline. And if that's true, then how many other limits in astrophysics are just rough estimates? What else are we getting wrong? And here's something even creepier. Some scientists think ultramassive white dwarfs could eventually collapse into strange matter. That's matter made of strange quarks, something totally exotic that doesn't behave like anything we know. If that happens, it could create a strange star, or even start a chain reaction that turns other stars into strange matter too. It sounds like science fiction, but it's an actual hypothesis being studied right now. And if that doesn't blow your mind, consider this. Ultramassive white dwarfs could be the ancestors of black holes that never formed. What if there are hundreds or thousands of these stars hiding out in our galaxy, just waiting for something, anything, to push them over the edge? A tiny collision, a sliver of gas, a magnetic flare. That could be enough to trigger collapse. And just like that, boom, black hole. No warning, no sign, just silent annihilation. Now think about our own Sunday. It's expected to become a white dwarf in about 5 billion years. Not ultramassive, just a regular one. But what if the sun isn't as ordinary as we think? What if there's something waiting in its core, something that could tip it into ultramassive territory? Maybe it doesn't take much. Maybe the difference between a normal white dwarf and an ultramassive one is razor thin, like walking on a wire between survival and collapse. It's not just about stars. It's about what the universe is made of. What the rules are. What happens when the rules don't apply. And we're only just starting to ask the right questions. The fact that these stars exist at all means we're missing something. And if we're missing something this big, what else are we not seeing? What other monsters are hiding in the dark corners of the galaxy, quiet and patient, waiting to be discovered? The more we learn about ultramassive white dwarfs, the more they look like cosmic glitches. Things that shouldn't be, but somehow are. And that's what makes them so haunting. They're not loud. They're not dramatic. They just exist. Quietly. Unapologetically. Breaking the laws we thought were unbreakable. They don't flash across the sky. They don't explode with fireworks. They just sit there in the dark, holding secrets inside them. Secrets that could change everything we think we know about stars, death, gravity, and the very makeup of reality itself. You have to understand, when astrophysicists first discovered these ultramassive white dwarfs, the reaction wasn't excitement. It was confusion. These objects weren't part of the plan. They weren't in the textbooks. It's like finding a boulder floating in the air and being told it's totally normal. No, it's not. It should fall. But it doesn't. And instead of accepting it, scientists now have to go back and ask questions we thought we'd already answered. What's a white dwarf, really? What are the limits of mass and pressure? Is our understanding of stellar death incomplete? And it gets even weirder. Some of these ultramassive white dwarfs aren't just bizarre because of their mass. It's their age. They're old. Older than expected. Some of them seem to have been sitting out there in space for billions of years, completely stable, when they should have done something, anything, by now. And that leads to a theory that's somehow even more mind-blowing. What if these stars didn't come from our galaxy at all? Think about this. What if ultramassive white dwarfs are relics of an ancient time? From a galaxy that merged with ours billions of years ago. Or even stranger, what if they're leftovers from a previous version of the universe? Could they have survived a cosmic reset? Could these be the corpses of stars from before the Big Bang as we know it? It sounds crazy, until you realize that we barely understand what the universe even is. Dark matter, dark energy, cosmic inflation, most of what makes up the cosmos is still a mystery. So who's to say these ultramassive white dwarfs aren't another piece of that hidden puzzle? Maybe they formed in regions of space where the rules are different. Maybe they're touched by dark matter in a way we don't understand. Some scientists have even speculated that dark matter might accumulate inside these stars, increasing their mass without triggering collapse. That could explain why they're so heavy. But it raises a new question. Is dark matter interacting with normal matter more than we think? And here's something else. If white dwarfs can grow this heavy and still stay intact, what does that say about the boundary between stars and black holes? Maybe the line isn't as sharp as we thought. Maybe there's a whole gradient of objects in between that we haven't fully identified yet. We know neutron stars sit between white dwarfs and black holes. But what about quark stars? Or preon stars? These are hypothetical stars made of particles even smaller than quarks. We don't know if they exist. But the existence of ultramassive white dwarfs makes the idea seem less far-fetched. So let's go back to that word. Limit. Science is full of limits. Speed of light. Absolute zero. Planck length. Chandrasekhar mass. These limits give us structure. They let us build models, equations, predictions. But every once in a while, the universe throws us an exception. And when that happens, it's not just a mistake, it's a message. It's the universe telling us, look closer. And when we look closer at ultramassive white dwarfs, we see a pattern of defiance. They defy the limits of mass. They defy gravity. They defy time. They spin too fast. They shine too long. They weigh too much. And through all of that, they hold steady. Now imagine this. One day, far in the future, an ultramassive white dwarf could slowly gather just a bit more material. Maybe a passing comet, or the last remains of a shattered asteroid. Just enough to tip it over the edge. And when that happens, it won't be gradual. It won't be gentle. It will collapse. Instantly. Into something no one's ever seen before. Not a normal black hole. Not a normal neutron star. But maybe something else. And here's the kicker, this collapse might not make any noise. No supernova. No blast. Just a flicker, and gone. A light winks out in the sky. And we might not even notice. We might only catch it years later when we check the same patch of sky and realize, wait, something's missing. That's the kind of cosmic horror these stars represent. They don't need to roar to be terrifying. They just need to exist. Because their existence means we don't understand the rules we live by. And if we don't understand the rules, what else are we missing? How many of these ultramassive white dwarfs are out there right now, floating between galaxies, beyond telescopes, waiting? And how many of them are already on the brink? And here's something wild. Some white dwarfs cool down so much over billions of years that they become what's known as black dwarfs. These are theoretical. We've never seen one. Because the universe isn't old enough for any white dwarf to have cooled that long. But in theory, they're cold, dead, barely radiating heat. Now imagine an ultramassive white dwarf that cools into a black dwarf, but with all that mass still packed inside. What happens then? Could it become unstable over time? Could quantum tunneling cause a sudden collapse billions of years later? Or could it turn into something else, something we've never imagined? Some physicists even speculate that black dwarfs might one day become the seeds for new universes. That if the right conditions are met inside them, the collapse could trigger something like another Big Bang, in a different realm of space-time. It sounds like fantasy, but so did the idea of black holes once. So did gravitational waves. So did white dwarfs themselves. So here we are. A star dies. It leaves behind a glowing ember. That ember is more massive than it should be. It doesn't collapse. It doesn't fade. It just waits. Maybe for eons. Maybe for a final moment that never comes. And we watch. And we wonder. And that is the real mystery. So now let's pull the curtain back even further and look at how we even discovered these ultramassive white dwarfs in the first place. Because it's not like they raise their hand and say, "Hey, I'm breaking the laws of physics." You have to be paying attention. You have to be looking in just the right way at just the right time, and even then, it's easy to miss what's in front of you. That's exactly what happened. Astronomers using data from space observatories like Gaia began to notice something odd. Some white dwarfs were simply too heavy. And not just by a little bit, some were tipping the scales close to 1.35 times the mass of the Sun. That might not sound like a lot, but for a white dwarf, it's insane. Because remember, the limit, the Chandrasekhar limit, is about 1.4 solar masses. And these things are brushing right up against that, but still staying white dwarfs. They're not collapsing. They're not blowing up. They're just sitting there. And that was the first red flag. When astronomers dug deeper, they found even more oddities. These ultramassive white dwarfs had extremely high surface gravity, up to 100,000 times stronger than Earth's gravity. If you somehow stood on one, you'd be crushed instantly. But that's not the part that blew scientists' minds. It was their radius. These objects were tiny. Not just small, absurdly small for their mass. That's when you realize how dense they really are. You could pack the mass of our entire Sun into a sphere the size of Earth, and still be in the realm of a normal white dwarf. But some of these ultramassive ones are even smaller than that. That's like folding reality in on itself. Then came the chemical puzzles. When researchers looked at the surface compositions of these ultramassive white dwarfs, they noticed something strange. Some of them had unusual levels of oxygen and neon, elements that suggest an origin very different from the typical white dwarf. You see, most white dwarfs are made of carbon and oxygen. But these ultramassive ones? They may be made of oxygen, neon, and even magnesium. That hints at something huge, that these might be the remnants of very massive stars that didn't go supernova. And that cracks open a whole new theory, failed supernovae. What if some massive stars don't explode like we thought they should? What if, instead of going out with a bang, they just quietly collapse into a white dwarf without all the fireworks? That would be like watching a balloon slowly deflate instead of popping. And it changes the whole picture of how stars live and die. But there's another idea, just as wild. Some scientists believe these ultramassive white dwarfs might actually be the result of two smaller white dwarfs colliding and merging. Think about that for a second. You've got two dead stars. They spiral into each other, smashing together in a cosmic crash. Most of the time, this would create a supernova. But what if, just once in a while, it doesn't? What if the merger is quiet, and the two cores fuse into one, forming a brand new, ultramassive white dwarf? And now here's the real twist. When white dwarfs merge, their combined mass can easily exceed the Chandrasekhar limit. So why don't they collapse immediately into black holes? One theory says they might be supported, temporarily, by extreme rotation. When two white dwarfs merge, they can spin like crazy, and that centrifugal force could hold off collapse for a while. It's like spinning a bucket of water overhead. As long as you spin fast enough, the water stays in the bucket. But once that rotation slows, gravity wins. That creates a ticking time bomb. These ultramassive white dwarfs might be stable for now, but eventually, as they lose angular momentum, collapse becomes inevitable. And what happens then? Maybe they collapse into a neutron star or a black hole. Or maybe, something else. Let's zoom out even more. If ultramassive white dwarfs are the result of white dwarf mergers, that means binary systems play a much bigger role in stellar evolution than we thought. We've known for a while that many stars are born in pairs. But now we're realizing that their entire afterlife might depend on whether or not they stay close to their partner. It's like cosmic romance, or cosmic tragedy, depending on how you look at it. And here's where things get disturbing. These collisions don't always end cleanly. Sometimes they trigger type I supernovae, massive explosions used as standard candles to measure distances across the universe. But what if some of those explosions aren't what we think? What if some of the standard candles we've been using to map the cosmos are actually liars? That would throw off our entire measurement of how fast the universe is expanding. Which means ultramassive white dwarfs might not just be weird stars, they might be sabotaging our entire cosmic model. Let that sit for a minute. And let's talk about temperature. Ultramassive white dwarfs tend to be hotter than average. That suggests they're younger, freshly formed from recent mergers. But here's the confusing part. Some of them are cool, indicating that they've been around for billions of years. How can they both be newborns and ancient relics? This brings us to another mind bender. What if there are multiple paths to becoming an ultramassive white dwarf? Some might be born from the quiet deaths of supermassive stars. Others might come from chaotic mergers. And some, this is the crazy part, might not even be made from normal matter at all. Yeah. Let's go there. There's a fringe idea that some ultramassive white dwarfs could contain or be influenced by dark matter. Not just surrounded by it, actually infused with it. Dark matter doesn't interact with light, so we can't see it. But it has gravity. If a white dwarf formed in a dense region of dark matter, it could slowly accumulate dark particles over time, adding mass without adding pressure in the usual way. That could explain how they get so heavy without collapsing. It's a wild theory, but not impossible. After all, we still don't know what dark matter even is. It's like trying to solve a puzzle without knowing what the pieces look like. Now let's consider what ultramassive white dwarfs could teach us about the end of the universe. We often talk about stars dying, galaxies fading, and everything cooling down into heat death. But what role do white dwarfs play in that story? A long one. White dwarfs, especially massive ones, are built to last. They don't fuse elements anymore, but they radiate heat for trillions of years. Eventually, they cool into black dwarfs, dark, dead stars drifting through eternal night. In the far, far future, like 10 to the power of 100 years from now, some theorists believe black dwarfs could undergo spontaneous collapse due to quantum tunneling. One moment stable, the next moment, boom. A new kind of supernova. A kind of quantum ghost popping back into action after the rest of the universe has gone still. And that collapse might be the last fireworks the universe ever sees. So when we look at ultramassive white dwarfs, we're not just seeing stars. We're seeing messengers from the future. Beacons from the past. Living contradictions. They're too heavy to exist. But they do. They should collapse. But they haven't. They come from explosions that didn't happen. From pairs that became one. From silence that should have been noise. Every single one of these stars is a puzzle the universe left behind, and right now, we don't have all the pieces. And that's why they matter. Because in a universe that feels infinite, ultramassive white dwarfs remind us that we still don't have all the answers. And maybe we never will. But the mystery doesn't stop at how ultramassive white dwarfs exist. What's even more haunting is the implication of their existence. Because if they're more common than we thought, then the models we've built for the life cycle of stars, models we've depended on for decades, might be missing something big. These aren't just rare flukes in a sea of predictable stellar corpses. They might be signs of a hidden process we barely understand. A secret pathway in the death of stars that could be quietly rewriting the rules of astrophysics, one invisible mass at a time. Now imagine this, somewhere out there, in a star system we've never seen, two white dwarfs have just finished their slow-motion dance. For millions of years, they've been circling each other, spiraling inward. And now, finally, they collide. But instead of exploding into a fiery supernova, they do something even stranger, they merge. Their cores press into each other, atoms collapse into tighter and tighter configurations, and what's left is a single object, a white dwarf so massive, so dense, it should be impossible. But it's not. It's real. It's quiet. And it's waiting. It might be the most dangerous object in its entire galaxy. Because one wrong nudge, maybe an accreting disk of material, maybe a planetary body falling into it, Or maybe just the inevitable decay of its spin over time, and that ultramassive white dwarf tips over the edge. The balance breaks. The core implodes. And in a fraction of a second, the most silent star in the galaxy becomes the loudest explosion it has ever seen. That's the kind of threat ultramassive white dwarfs might carry. They don't shout, they whisper. They wait. Let's look at one of the most famous candidates ever found, REJ 0317-853. This one is wild. It has about 1.35 times the mass of the Sun, but its radius is just about 3,000 kilometers. That's smaller than the Moon. And it spins fast. It completes one full rotation every 725 seconds. That's like having a sun's worth of mass packed into a moon-sized object, spinning faster than a record on a turntable. If that's not insane, I don't know what is. But here's where things get even more messed up. REJ 0317-853 also has a magnetic field about 300 million times stronger than Earth's. That's not a typo. Magnetic fields this powerful can tear apart atoms, distort electrons, and mess with the very structure of matter. In fact, the physics inside ultramassive white dwarfs might not even follow the rules we've written for normal matter. Because at that density, everything changes. Electrons are smashed so tightly into atomic nuclei that pressure no longer behaves like we expect. Quantum mechanics begins to dominate, but even that might not be enough. If you go too far, you start to compress electrons into protons, creating neutrons, and now you're not a white dwarf anymore. You're on the way to becoming a neutron star or something even worse. But what if there's something in between? A class of objects we haven't even named yet? Some astrophysicists are toying with the idea that ultramassive white dwarfs might be the missing link in the chain between white dwarfs and neutron stars. They don't fit cleanly into either category. They're too massive for one, not massive enough for the other. And yet they exist. That's the cosmic equivalent of finding an animal that's half wolf, half whale, and realizing the whole story of evolution needs to be rewritten. And now let's bring up something that almost no one talks about when discussing white dwarfs: gravitational waves. When two white dwarfs spiral into each other, they release gravitational ripples through space-time. LIGO has already detected these ripples from black hole mergers and neutron stars. But what if we could start catching the signals from merging white dwarfs, especially ultramassive ones? That would change the game. Because gravitational waves don't lie. They don't get absorbed by dust or confused by light. They're pure. They give you the raw blueprint of what's happening. And if we can capture them from white dwarf mergers, we might start to understand how many of these ultramassive remnants are forming. It would let us do something astrophysics hasn't been able to do very well until now: predict danger before it happens. Imagine knowing which systems in the sky are ticking time bombs. Which stars might collapse tomorrow, or in 1,000 years. That's not just science fiction, that's where astronomy is headed. But wait. Here comes another twist. Some researchers believe that ultramassive white dwarfs may actually evolve differently over time compared to typical white dwarfs. Because of their insane gravity and magnetic fields, the cooling processes may slow down, or even get disrupted. That means they stay hot longer, shine longer, and leave behind different chemical signatures. So if we find white dwarfs that are cooler than expected for their age, or with strange atmospheres, we might be looking at one of these monsters in disguise. They're like wolves in sheep's clothing, burnout stars pretending to be harmless, but hiding more mass and energy than you could possibly guess from just looking at them. Now let's talk about what these stars feel like, not scientifically, but viscerally. Think about standing near one. Just in theory. You're not on it, because if you were, you'd be dead before you even touched the surface. The gravity would pull every atom of your body apart. Your bones would flatten, your blood would vaporize, and your body would collapse into a paper-thin pancake. Not even light behaves normally around them. Light bends, curves, struggles to escape. And then there's the silence. Ultramassive white dwarfs don't pulse like neutron stars. They don't roar like quasars. They're just there. This quietness is part of what makes them terrifying. You could be staring directly at one through a telescope and never know what it's capable of. Because it looks boring. Like a faint dot in the sky. But behind that dot is something with the power to end itself in a flash so violent it could outshine its whole galaxy for weeks. The universe hides its greatest dangers in the most unassuming places. And that brings us to the idea of black dwarf supernovae. This one is way out there. It's not proven, but it's gaining traction. The idea is that in the far, far future, when white dwarfs cool and become black dwarfs, something bizarre might happen. Quantum tunneling could cause iron in their core to suddenly fuse. That would trigger a chain reaction, and a massive explosion. A supernova, not from a dying star, but from a star that's been dead for trillions of years. If that's true, ultramassive white dwarfs are the seeds of chaos planted deep into the future. A future we won't live to see. But let's not get ahead of ourselves. There's still so much we don't know. How many ultramassive white dwarfs are out there? Are they forming right now? Are they mostly hidden in other galaxies, too faint to see? Are some of them actually already collapsing, right now, into black holes or neutron stars without us noticing? Because here's the creepy part. We might not see it happen. If one collapses into a black hole, it might not produce a supernova at all. It might just vanish. A star, there one moment, gone the next. Silent. Sudden. And unless you're looking right at it, you'd never know. How many have already disappeared? And now think about this. If an ultramassive white dwarf collapses silently into a black hole, it might not even leave a trace. No light. No gravitational wave. No explosion. Just a sudden absence where a star used to be. A vanishing act so perfect it could fool our best telescopes. So what does that mean for the night sky we look at every night? It means some of the dots of light we're seeing might already be gone. What we're looking at could be ghosts. Remnants of stars that have already crossed a line we can't yet detect. There's a haunting thought buried in that idea. The night sky is not a snapshot of now. It's a graveyard of light from things that may no longer exist. So let's bring it back. Let's go even deeper. What makes ultramassive white dwarfs truly terrifying is that they force us to rethink not just stellar physics, but the entire cosmic timeline. These aren't just weird leftovers from stellar death, they're markers. They sit at the very edge of collapse. Too small to be neutron stars. Too big to be normal white dwarfs. That makes them liminal objects, caught in a cosmic in-between. And anything that sits on a threshold like that? It's unpredictable. Here's something that's baffling researchers even now. How stable are these things, really? Because they're balanced on such a razor's edge of gravity and electron pressure that even tiny changes, like a slight increase in temperature, a loss of angular momentum, or a sudden accretion of extra material, could tip them over. It's like trying to balance a bowling ball on the tip of a pencil. It's fine for a moment, maybe. But eventually it's going down. And that means they could be ticking clocks. Cosmic countdowns. Maybe not loud. Maybe not visible. But running out of time, all the same. What if we've been thinking about type I supernovae all wrong? Traditionally, we think they come from normal mass white dwarfs that reach the Chandrasekhar limit and detonate. But maybe, just maybe, a subset of these explosions comes from ultramassive white dwarfs collapsing in a totally different way. That would mean we've misunderstood a whole category of supernovae. And if that's true, the consequences ripple through everything, because type I supernovae are used to measure cosmic distance. They're how we figured out that the universe is expanding faster and faster. So what happens if we've been using unreliable rulers? The entire field of cosmology could be sitting on shaky ground, built on the assumption that every white dwarf explosion is the same. But if ultramassive white dwarfs are detonating differently, with different brightnesses or different timings, then all our maps of the universe might be off. Distances could be wrong. Timelines could be skewed. Expansion rates could be miscalculated. The implications are massive. Not just for stars, but for the entire structure of the cosmos. Let's pause for a second and appreciate how insane that is. One object. One weird type of stellar corpse. And suddenly, our entire picture of the universe becomes uncertain. That's the kind of power ultramassive white dwarfs hold, not just gravitationally, but philosophically. They challenge our sense of certainty. They remind us that even in the quietest parts of the sky, chaos might be lurking. Now here's a strange twist you probably didn't expect. Ultramassive white dwarfs could help us find alien civilizations. I know, it sounds like science fiction, but think about this. They're so rare, so bizarre, and so clearly formed through unusual means, that their presence in certain star systems might be a red flag. A red flag for artificial intervention. Let me explain. If advanced civilizations have the ability to manipulate stellar evolution, to guide the collapse and merger of stars for energy harvesting or cosmic engineering, then ultramassive white dwarfs might be byproducts of that. In fact, some have proposed the idea that unnatural white dwarf masses could be signs of alien megastructures gone wrong, or remnants of failed stellar experiments. It's a fringe idea, but not impossible. After all, what better place to hide signs of intelligent life than in objects we barely understand? If you want to bury your work in plain sight, you put it where no one is looking. And right now, hardly anyone's looking at ultramassive white dwarfs. Which brings us to another hidden puzzle. How old are they, really? Because one weird thing about white dwarfs is that their cooling rate depends on mass. More massive white dwarfs cool slower, but they also form faster. So, technically, ultramassive white dwarfs might be some of the oldest objects in the universe. They might have formed when the galaxy was young, back when things were hotter, denser, and messier. They've been cooling ever since. Sitting in silence. Watching. That puts them in a strange position, ancient observers of cosmic history. What have they seen? What galactic collisions have they survived? What dark matter clouds have they passed through? What gravitational influences have they resisted? Their existence could be a map of galactic memory, written in mass and magnetism. There's also the question of where these ultramassive white dwarfs tend to hide. Interestingly, many of them have been found in binary systems. That suggests mergers. But here's something really strange. Some of them appear to be isolated, with no obvious partner. So where did their companion go? Did it get absorbed? Was it flung away? Did it explode? Or are we simply not seeing it because it's a black hole now? This opens up a wild possibility, that ultramassive white dwarfs could sometimes be found in binary systems with hidden black holes. Invisible companions orbiting them silently, warping space with their presence but giving off no light. Just gravity. Just distortion. If we find more of those systems, we could be looking at one of the most exotic types of binaries in the galaxy. Dead stars dancing with even deader stars. And it doesn't stop there. Let's not forget about the strange case of magnetic braking. This is where a white dwarf, spinning fast, slows down over time because of its magnetic field interacting with the surrounding space. This loss of rotational energy could, over a long enough period, destabilize an ultramassive white dwarf. That's right. The very thing keeping it stable, its spin, could decay, and eventually boom. Collapse. Catastrophic explosion. So if you're wondering what causes these monsters to blow up, this could be a big piece of the puzzle. Not accretion. Not collisions. Just time. Just spin decay. A slow winding down into death. And if that's true, then some of the most dangerous white dwarfs aren't the ones we're watching right now, they're the ones we're not watching. The ones quietly ticking down in dark corners of the galaxy, waiting for the moment their spin drops just a little too far. One tick. One wobble. One spark. And then the end. And now imagine the kind of explosion that could happen when an ultramassive white dwarf finally loses that last bit of stability. We're not talking about a normal star's death rattle. This isn't a red giant puffing off its layers in a lazy farewell. This is a core that's been building tension for millions, maybe billions of years. A core that's already on the brink of what physics can handle. When it finally lets go, it could be a detonation that sends shockwaves across light years. A flash so bright it outshines the entire galaxy for a few seconds. That's not just dramatic, it's dangerous. The kind of energy released in a collapse like that could strip atmospheres from nearby planets. It could fry anything within a few light years. If there are civilizations orbiting stars near one of these ultramassive white dwarfs, their sky might suddenly erupt without warning. One moment they're going about their day. The next, every sensor lights up. Then silence. That's it. Game over. So now, think about what that means on a larger scale. These things are rare, but they're not that rare. And as we improve our telescopes, we're finding more of them. That suggests there could be hundreds, maybe thousands, scattered across the Milky Way. Some are probably stable. Some aren't. Some are right on the edge. We might be living in a galaxy filled with silent bombs. White dwarfs used to seem like peaceful objects. Cold, quiet remnants of stars. But ultramassive white dwarfs are more like cosmic landmines. Waiting. Waiting for time, or physics, or just bad luck to set them off. And if that wasn't enough, there's another twist. Let's talk about crystal cores. Yes, crystals. As white dwarfs cool, their interiors begin to crystallize. That means the carbon and oxygen inside starts forming a solid structure, like a diamond. That's not metaphorical. It's real. If you were to somehow scoop out the heart of a white dwarf, it would be an enormous space diamond. Not shiny, not pretty, but solid carbon, hard as anything. But here's where it gets weird for ultramassive ones. Because of their mass, their internal pressures are off the charts. That changes how the crystallization happens. The atoms inside are so crushed together, they can form superionic structures, a weird, semi-solid state of matter that doesn't even behave like normal solids. Think of it as matter frozen in place but with ions that can still move around. It's not quite a fluid. Not quite a solid. Just weird. This superionic phase might change the way ultramassive white dwarfs cool. It could even trap heat inside for longer than we thought, which would throw off all our models for how fast they evolve. That means we might be misdating them by billions of years. We might be looking at something that appears young, but is actually ancient. And what does that say about our understanding of star populations? If we can't even tell how old these stars are, then we can't accurately map how galaxies evolve. We can't tell when certain regions formed stars. We can't tell how fast the galaxy is aging. Ultramassive white dwarfs might be throwing off our entire understanding of galactic history, just because they don't cool like we thought they did. And again, it's all happening in silence. No noise. No outbursts. Just a star that looks like it's frozen in time, while deep inside, quantum forces are battling against gravity, magnetism, and rotation. Even their magnetic fields are scary. Some ultramassive white dwarfs have magnetic fields that are hundreds of millions of times stronger than Earth's. That kind of field could strip electrons from atoms, twist the shape of molecules, and generate intense radiation belts. If one of these stars had planets, those planets would be bathed in radiation. No life as we know it could survive. But even from far away, that magnetic field might mess with things. It could affect the motion of nearby charged particles. It could distort the plasma in interstellar space. It might even have an influence on nearby stars. It's like a magnet the size of the moon, floating out there in the dark, silently warping everything around it. And then there's the X-rays. Because of their high mass, these white dwarfs can sometimes pull in material from nearby sources, especially in binary systems. And when that happens, you get X-ray bursts, brief, powerful flashes of energy. These aren't just interesting, they're dangerous. X-rays from a single burst could irradiate anything nearby, trigger chemical reactions in planetary atmospheres, and even create biological mutations. And the thing is, we don't always see these bursts coming. They're short, random, unpredictable. It's like the white dwarf just loses its grip for a second, then flares up. And then back to silence. It's the unpredictability that makes them so dangerous. You don't know when they'll break. You don't know when they'll explode. And worst of all, you don't know if one's already exploded, and the light just hasn't reached us yet. So now we come to maybe the strangest part of all. If ultramassive white dwarfs are rare, powerful, and potentially universe-altering, why aren't we talking about them more? Why aren't they in every astronomy book? Why aren't they part of every conversation about star death? The answer is unsettling, because we only just started noticing them. That's it. Our telescopes weren't powerful enough before. Our models weren't detailed enough. And because they don't behave like regular white dwarfs, they slipped through the cracks. We were looking at them for decades, and didn't realize what they were. And that begs the question, what else are we missing? Because if an object this massive, this weird, and this important could hide in plain sight for so long, what else might be out there, waiting for us to look closer? What other monsters are hiding in the quiet? What else in the universe is stranger than we ever imagined? And now let's go deeper, because we've only just scratched the surface of what ultramassive white dwarfs could mean not just for astrophysics, but for the very fabric of the cosmos. Let's rewind to one of the most chilling possibilities, the idea that some ultramassive white dwarfs are ticking time bombs. Specifically, some could cross that invisible line, the Chandrasekhar limit. That's supposed to be around 1.4 times the mass of our Sun. Once a white dwarf gets even slightly heavier than that, it shouldn't stay a white dwarf at all. It should collapse into a neutron star or explode as a Type Ia supernova. But here's the mystery, we've found white dwarfs heavier than that, and they haven't exploded. That doesn't make sense. At least not according to the rules we thought we knew. So the question becomes, why? What's holding them up? And there's a possible answer that sounds like something straight out of science fiction, but it's rooted in the bizarre realm of quantum physics, something called rotation support. Imagine you spin a pizza dough. As it spins, the dough spreads out and holds its shape. Now think of an ultramassive white dwarf. It might be spinning so fast that the outward centrifugal force is pushing against gravity just enough to stop it from collapsing. It's like the spin itself is buying it time, stabilizing it. But the moment it slows down even a little, maybe through magnetic braking or gravitational waves, it could collapse in seconds. That's not just terrifying. That's completely unpredictable. And even more fascinating? Some of these ultramassive white dwarfs are rotating fast enough to flatten slightly at the poles. That distortion changes their gravitational field. It changes how light bends around them. It changes how nearby stars orbit. It even changes the behavior of the particles in their atmospheres. These aren't smooth, spherical stars. They're spinning, distorted, ultra-dense monsters. But rotation is only one piece of the puzzle. Another reason they might be surviving above the Chandrasekhar limit? Magnetism. Strong magnetic fields don't just affect external radiation. Inside the core, they might be rearranging the physics. We're talking about altering the equation of state of matter, changing how atoms and electrons interact under intense pressure. Basically, magnetic fields could be creating a new balance. A freak balance. A balance that only exists in a razor-thin window of parameters. That window could close at any moment. Which leads to another huge cosmic question. What if some ultramassive white dwarfs don't go supernova at all? What if they collapse straight into neutron stars? Or even stranger, black holes? That changes everything. Because we've always assumed that black holes form from giant stars. But now, we might be seeing a totally different origin. A low-mass pathway to a black hole. A star that lived a calm life, died quietly, and still managed to become one of the most extreme objects in the universe. That means the population of black holes in the galaxy might be way higher than we thought. Not from supernovae. Not from giant explosions. Just quiet collapses. Quiet transitions. Silent killers. And that also means the death of these stars might not light up the sky. They might just wink out. One moment visible. The next gone. No flash. No warning. No debris. Just collapse. And now you might be wondering, how do we even find these things? Well, that's part of the challenge. Ultramassive white dwarfs are faint. They don't shine brightly like other stars. They don't give off huge bursts of radiation unless they're in binary systems. That means many of them are hidden in the dark, drifting through the galaxy. They're so small, maybe the size of Earth, that even if they're close by, They're incredibly hard to spot unless you're looking straight at them. Some might be lurking just a few hundred light years away, and we'd never know. Now add this to the mix: mergers. Two white dwarfs in a binary system can spiral toward each other over millions of years, losing energy through gravitational waves. Eventually, they crash together. That crash could create an ultramassive white dwarf. But here's where it gets weird again. If the merged object doesn't explode right away, it could just sit there, heavier than the Chandrasekhar limit, defying physics. These post-merger objects are often unstable. Their interiors churn with chaotic rotation, unbalanced magnetic fields, and massive heat. They might last for centuries. Or minutes. And what if some of them already exploded, and we saw those as bright Type I supernovae, but never knew their origin? That's one of the mysteries. We've seen Type I supernovae for a long time. We use them to measure distances across the universe. But we've never been totally sure what causes them. We think they come from white dwarfs exploding, but the exact process is still debated. Ultramassive white dwarfs might be the missing piece. But that opens another problem. If we've been using Type I supernovae to measure how fast the universe is expanding, and if we've misunderstood their causes, then our measurements might be wrong. That's massive. It could mean the entire framework we use to understand the expansion of space, the rate of acceleration, the behavior of dark energy, could be built on shaky assumptions. That's the butterfly effect of astronomy. One little star, breaking one little rule, could ripple out to the edge of the cosmos. And we're only now catching up to that idea. New surveys, like those using the Gaia spacecraft and deep sky infrared imaging, are turning up white dwarfs we never knew existed. Some of them are right in our galactic neighborhood. Some are ultramassive. And some are behaving in ways that just don't add up. For example, one ultramassive white dwarf, about 1.35 times the mass of the Sun, was recently found spinning so fast and with such an intense magnetic field that its atmosphere is permanently distorted. Its poles are brighter than its equator. Its surface is torn between gravity and magnetism. And it might be shedding mass in unpredictable ways. Another one has been found with an unusually thin atmosphere, almost like it's being stripped by unseen forces. Scientists think it might be leaking particles into interstellar space. Slowly. Quietly. Almost like it's disintegrating. Not exploding. Just fading. And that's a terrifying idea, the slow death of a star not through fire or collapse, but through leakage. A ghost star bleeding into the void. And yet, we wouldn't know. We can't feel it. We can barely measure it. That's the universe's secret weapon, silence. And here's where things start to feel almost personal, even haunting, because these ultramassive white dwarfs might not just be far-off curiosities. They could be our galaxy's quietest threats. Think about this. The universe isn't loud. It doesn't announce when something big is about to happen. Most of the time, the most dangerous things don't make a sound. They just change everything, without warning. A supernova is bright and dramatic, but a white dwarf quietly crossing the tipping point. That's invisible. Silent. Sudden. It's like living next to a dormant volcano that never shows signs of pressure, then one day, it just disappears into itself or takes half the sky with it in a flash. And what really messes with your head? We have no idea how many of these ultramassive white dwarfs are out there. They're small, dim, and spread across billions of stars. Every time we point a better telescope at a new patch of sky, we find more white dwarfs than we expected. And every once in a while, one of them is just too heavy. So the question grows louder. Are we seeing the full picture of stellar death, or just the parts that shout the loudest? That's where the research gets weird, because ultramassive white dwarfs don't seem to obey the same rules as others. Normally, white dwarfs cool down over billions of years. They fade gradually, becoming black dwarfs, dead, cold remnants of stars. But with ultramassive ones, cooling doesn't always match up. Some cool faster. Some cool slower. Some maintain their heat for far longer than they should, suggesting unknown processes happening in their cores. And what could be powering that? One theory, Crystallization. Yeah, we're talking about stars turning into cosmic diamonds. See, as white dwarfs cool, the ions inside them start to slow down. Eventually, those particles arrange themselves into a crystal structure. It's like the star's core is freezing, not in a cold way, but in a molecular alignment way. This crystallization process releases latent heat, slowing the star's cooling. It's been observed in normal white dwarfs. But with ultramassive ones? It might be on another level. Their entire cores could be crystallized, essentially turning them into enormous, dense diamond-like structures the size of Earth. Imagine that. A diamond planet floating in space, built from the remains of a dead star, weighing more than a sun, invisible unless you know exactly where to look. And because of how intense their gravity is, this crystallization might happen faster and more violently than in lower-mass white dwarfs. The interior of the star might literally fracture and quake as it solidifies. And if it reaches a critical density during this process? Boom! Collapse. This is where theoretical physics gets wild. Some researchers believe that deep inside the most massive white dwarfs, matter could be transforming into exotic states, like strange matter or quark gluon plasma. These are forms of matter that don't normally exist in the universe, except in the hearts of neutron stars or just after the Big Bang. If these transitions happen inside an ultramassive white dwarf, it might not just become a neutron star, it might become something we've never seen before. There are even theories that if a white dwarf gains just enough mass in just the right way, through slow accretion or magnetic stabilization, it could bypass the neutron star stage entirely and collapse straight into a black hole. No light. No supernova. Just gravity winning. This possibility, if real, would break what we thought we knew about stellar evolution. It would mean that not all stars need to go supernova to become black holes. And that would throw a wrench into every simulation of galactic evolution we've ever made. Because all those models? They rely on predictable life cycles, predictable explosions, predictable deaths. Ultramassive white dwarfs aren't predictable. And maybe that's why they're so important. Because they remind us that the universe isn't finished surprising us. It's still hiding things in plain sight. Things that defy rules. Objects that shouldn't exist, but somehow do. Let's get even deeper into the quantum side of this mystery. At the heart of every white dwarf is electron degeneracy pressure, the thing that holds the star up. It's a quantum effect that basically says electrons can't be squeezed into the same space. They push back. It's like a cosmic no-go zone. But in ultramassive white dwarfs, the gravity is so strong that this pressure is being pushed to the edge. Electrons are moving at nearly the speed of light just to maintain balance. That's not a metaphor. That's real physics. If they moved any faster, they'd break the laws of relativity. It's like watching a rope stretch tighter and tighter, with every atom in the star holding its breath. If anything disturbs that balance, if the star cools, spins slower, gains even a tiny bit more mass, it could snap. And the whole thing collapses. Now imagine this happening in a binary system. An ultramassive white dwarf sitting next to another star, maybe a red giant. As the red giant swells, it spills matter onto the white dwarf. That's called accretion. If enough material falls in, the white dwarf passes the Chandrasekhar limit. And what happens then? If conditions are just right, it explodes in a Type I supernova. But if they're not, if the star is spinning fast enough or magnetic fields stabilize it, it might hang on just long enough to delay the inevitable. Until one day it can't. And the collapse doesn't create a bright explosion. It just turns dark. No warning. No flash. No sound. Just one more invisible black hole. What makes this all even more unnerving is that white dwarfs can sit in this suspended state for millions of years. Long enough that we could see them, think they're safe, and be totally wrong. Some of the ultramassive white dwarfs we've already cataloged might be at the edge of collapse right now. And we wouldn't know. We'd only find out after the fact, when a new black hole appears out of nowhere. Or a gravitational wave shakes detectors on Earth, coming from a region of the sky that looked completely ordinary. And still, We barely understand how these ultramassive white dwarfs form in the first place. Are they born this way from unusually massive stars that somehow skip going supernova? Or are they products of white dwarf mergers, where two average stars combine into something far heavier? The merger theory is gaining ground, especially with gravitational wave detections becoming more common. The LIGO and Virgo observatories have already spotted compact object mergers. Some of those signals might not have come from neutron stars or black holes. Some might have come from white dwarfs colliding and merging, quietly, in the dark, with only a whisper of light and a long sigh of gravitational energy. This is the realm we're stepping into now. A world where light is no longer the only tool we use. A world where we're listening for ripples in space-time, reading the magnetic fingerprints of dying stars, and tracing the gravitational footprints of objects that don't glow at all. Ultramassive white dwarfs are like puzzles with missing pieces. Every time we think we've figured out the rules, one of these things shows up and breaks them. And maybe that's the point. They're here to remind us that space isn't just empty. It's full of strange survivors, hidden monsters, and silent engines of destruction. And when you really stop and think about that, about these massive, silent stars just floating out there, holding on to the last shreds of stability, it hits you. The universe isn't just made of chaos and fire. It's also built on tension. Delicate, invisible tension. And ultramassive white dwarfs? They are tension made solid. Objects holding together by the thinnest margin, existing in a cosmic waiting game. It's not just physics. It's poetry. But let's go even further. One thing that truly stuns scientists is the sheer density of these stars. A typical white dwarf already has a mass similar to our Sun, crushed into something the size of Earth. But with ultramassive white dwarfs, say, 1.3 to 1.4 solar masses, the density is pushed to another level. We're talking about material so tightly packed that a single cubic centimeter, about the size of a sugar cube, could weigh hundreds of thousands of tons. That's not an exaggeration. That's real. It's like compressing Mount Everest into a suitcase. That's the level of density we're dealing with. And here's what makes that so strange. Our current understanding of matter starts to break down under that kind of pressure. The atoms inside the star are no longer acting like normal atoms. The electrons are being pushed into protons, forming neutrons in a process that should, in theory, begin the transformation into a neutron star. But some ultramassive white dwarfs seem to stall at the edge of that change. It's like the star is saying, "Not yet." This creates a kind of stellar limbo, a state that isn't quite a white dwarf and isn't yet a neutron star. Some scientists have even coined the term preon stars, or exotic matter remnants, for these in-between objects that might exist only briefly or be hiding in plain sight. And if these objects do exist, they might hold the key to unlocking some of the biggest cosmic questions we've ever asked. Take dark matter, for example. We still don't know what dark matter is. We know it's out there, holding galaxies together, bending light, shaping the universe, but we can't see it or touch it. But what if some of that dark mass is hidden in objects like ultramassive white dwarfs? Objects so dense and dim that they've evaded detection? It's possible. Or even more intriguing, what if the material inside ultramassive white dwarfs begins to behave like dark matter itself? Imagine matter that, under immense gravitational pressure, changes its properties. Stops interacting with light. Stops behaving like normal matter. Starts bending the rules. That might sound like science fiction, but it's not off the table. The deeper we look into quantum physics and gravitational physics, the more we realize that the universe isn't binary. It's not just stars and black holes. It's a spectrum. A continuum of strange, in-between states where the rules are blurred. Ultramassive white dwarfs sit right at that edge. And their magnetic fields? Another mind-bender. Some of these stars have surface magnetic fields billions of times stronger than Earth's. Let that sink in. A magnetic field so powerful, it could rip apart molecules, distort atomic orbits, and potentially warp nearby space-time. These are not mild little dead stars. They're monstrous magnetic machines, pulsing silently in the dark. And when these fields interact with nearby stars or surrounding gas, they can unleash bursts of energy. Not enough to be called explosions, but enough to send out X-rays, gamma rays, and even radio waves. Sometimes we catch these flashes and wonder, what just happened? And often we have no clue. But ultramassive white dwarfs are a strong suspect. They might even be the culprits behind some of the universe's weirdest events, like fast radio bursts, FRBs. Those are intense, millisecond-long blasts of radio energy that seem to come from random parts of the sky. Some repeat. Some don't. And nobody knows why. But here's the theory. When an ultramassive white dwarf's magnetic field twists too much, it can suddenly snap, releasing a burst of energy in the process. Almost like a stark wake. If that burst hits Earth, we hear it as a brief, sharp radio signal. And since ultramassive white dwarfs are hard to see, they'd be the perfect hidden trigger. They wouldn't leave a trace. Just that strange flash, and silence. Now imagine a whole galaxy filled with these things. Quiet. Invisible. Waiting. And that's not just a thought experiment. It's becoming more and more likely. In fact, some astronomers think that ultramassive white dwarfs might make up a significant percentage of the so-called dark stars we've cataloged, objects that don't shine but exert gravity. We've spotted hundreds of stars whose motions suggest there's something massive nearby, but we can't see anything. Could they be orbiting ultramassive white dwarfs? We might be surrounded by these things and not even know it. And if they're close enough to Earth, within a few hundred light years, it raises even more questions. Like, could their gravity affect our solar system over long timescales? Could they be responsible for strange orbital anomalies in outer planets or comets? It's a long shot, but not impossible. And while we're on the subject of proximity, let's talk about Sirius B. It's one of the most famous white dwarfs, and it's in a binary system with Sirius A, the brightest star in the night sky. Sirius B is a white dwarf that's been extensively studied. But some recent models suggest it might be heavier than we originally thought, bordering on ultramassive territory. And it's only 8.6 light-years from Earth. That's practically next door, in cosmic terms. If Sirius B is indeed ultramassive, or if there are others like it even closer, it means we're not just looking at distant mysteries. We're living among them. These objects are here. Real. Near. And constantly evolving. They could collapse. They could explode. They could silently bend space around them, affecting time and light in ways we haven't fully grasped yet. And what's maybe most incredible of all, we're only just beginning to understand them. Astronomy used to be about looking at bright things. Suns. Galaxies. Nebulas. But now, the future of astronomy might be in the dark. In the invisible. In the things that don't shine, but weigh more than entire solar systems. Ultramassive white dwarfs are part of a new class of cosmic object. Not bright enough to be noticed easily. Not massive enough to collapse on sight. But weird enough to break the rules. And in a universe built on rules, the rule breakers are the ones worth watching. They might just be the key to everything. Now, while ultramassive white dwarfs already sound like something straight out of a science fiction novel, their existence also challenges some of the very foundations of physics. One of the core ideas behind white dwarfs is something called the Chandrasekhar limit. This is basically the maximum mass a white dwarf can have before it can no longer support itself against gravity and collapses into something denser, usually a neutron star or a black hole. This limit sits around 1.4 times the mass of our Sun. So when we talk about ultramassive white dwarfs, we're referring to stars that hover extremely close to that boundary. Scientists used to think nothing could surpass the Chandrasekhar limit without collapsing. But recent observations suggest there might be white dwarfs heavier than that limit. This is puzzling. How do they hold up? What's stopping gravity from crushing them into oblivion? The answer might lie in something unexpected: their internal composition and the physics under extreme conditions. One idea is that inside these ultramassive white dwarfs, the particles might behave in ways that ordinary matter does not. The electrons that provide the pressure to resist gravity, called electron degeneracy pressure, might behave differently when squeezed to such extremes. Quantum mechanics steps in and suggests that at these densities, the physics might change in subtle ways that allow the star to stay stable a bit longer than expected. There might even be exotic particles inside, or forces we haven't fully discovered yet. This is why ultramassive white dwarfs are not just stars, they're laboratories for fundamental physics. The more we look, the more we realize that the universe is stranger than we imagined. The exact composition of these stars might include heavier elements like neon, oxygen, or magnesium, rather than just carbon and oxygen, which are typical for smaller white dwarfs. The presence of these heavier elements affects the star's structure and stability in complex ways. Scientists also use computer models to simulate what might happen inside these stars. These models suggest that ultramassive white dwarfs could be the final evolutionary stage for certain kinds of stars, ones that started out much heavier than our Sun but lost a lot of mass during their lives. If true, these stars give us a glimpse into how stars live and die, and what might happen in the final moments before some of the most violent cosmic events. Speaking of violent events, ultramassive white dwarfs might also be connected to one of the universe's most famous explosions, Type Ia supernovae. These are massive explosions bright enough to be seen across billions of light years. They play a huge role in measuring the expansion of the universe. The traditional idea is that a white dwarf reaches the Chandrasekhar limit by stealing matter from a nearby star, then explodes. But what if some ultramassive white dwarfs hover right at the edge, and only under certain conditions explode? Maybe some don't explode at all but instead collapse quietly, or undergo other mysterious transitions. This opens a new door into understanding cosmic explosions and the life cycles of stars, and it forces astronomers to rethink how these supernovae work. Another fascinating mystery around ultramassive white dwarfs is their role in gravitational waves. These ripples in spacetime, predicted by Einstein and confirmed by experiments only in the past decade, come from cataclysmic events like black hole mergers and neutron-star collisions. But ultramassive white dwarfs and binary systems might also be sources of weaker, continuous gravitational waves that are harder to detect but carry crucial information about their mass, spin, and magnetic fields. If we manage to detect these gravitational waves from ultramassive white dwarfs, it could give us a direct look inside these stars, a kind of cosmic ultrasound revealing their inner workings. And the more we learn about these stars, the more questions pop up. Like, what is the lifespan of an ultramassive white dwarf? How long can they remain stable before collapsing? Could they be responsible for other unexplained cosmic phenomena? How common are they across the universe? Could some of the mysterious, missing mass in galaxies actually be ultramassive white dwarfs? Answering these questions means pushing the boundaries of technology and theory. New telescopes, new detectors, and new computational methods are being developed all the time to hunt down and study these elusive objects. One exciting frontier is the use of X-ray and ultraviolet telescopes, which can pick up the faint emissions from ultramassive white dwarfs. Their intense magnetic fields sometimes produce unique signatures that can be spotted across the galaxy. Some astronomers are even considering the possibility that ultramassive white dwarfs could be a missing piece in the puzzle of dark matter, or at least a part of the explanation for some of the invisible mass in the universe. While they can't explain all of it, the sheer number of these stars, if they exist in large amounts, might contribute significantly. So, when you look up at the night sky, remember, there are these silent giants out there, remnants of ancient stars, holding on to existence at the edge of physics. They're not just leftovers. They're keys. Keys that could unlock the deepest secrets of how matter behaves, how stars live and die, and how the universe itself is structured. Ultramassive white dwarfs force us to rethink what's possible. They invite us to explore a universe stranger than we imagined, where the lines between physics and mystery blur, and where every new discovery opens up even more questions. And that's exactly why we keep looking. Because space is a never-ending story, and ultramassive white dwarfs are one of its most thrilling chapters. Digging even deeper into ultramassive white dwarfs, we have to talk about how we find them in the first place. Detecting any white dwarf is tricky because they're incredibly faint compared to other stars. They've used up most of their fuel, so they no longer shine brightly like our Sun. Instead, they slowly cool and fade over billions of years. Ultramassive ones are even harder to spot because, despite their mass, they can be quite small in size, only about the size of Earth, packed with matter at unimaginable density. One of the key ways astronomers identify ultramassive white dwarfs is by measuring their mass and radius. Mass is figured out by observing how they affect nearby stars or through their gravitational pull, especially if the white dwarf is part of a binary system. Radius comes from studying the light they emit and using models to estimate size based on temperature and brightness. When you put those two together, if the mass is close to or above the Chandrasekhar limit and the size is very compact, you might have an ultramassive white dwarf. But this method isn't perfect. There are uncertainties in measurements, and sometimes what looks like an ultramassive white dwarf might turn out to be something else entirely, like a neutron star or a smaller black hole masquerading as a white dwarf. This is where advancements in telescope technology and data analysis come into play. Instruments like the Gaia Space Observatory, launched by the European Space Agency, have revolutionized our ability to map stars in our galaxy with extreme precision. Gaia's detailed measurements of distance, brightness, and motion have led to the discovery of several promising ultramassive white dwarf candidates. What makes these discoveries exciting is not just the stars themselves but what they tell us about the history of our galaxy. Ultramassive white dwarfs are the endpoints of stars that started out very heavy, but for some reason, didn't collapse into black holes or neutron stars. This suggests unusual stellar evolution paths or special conditions in binary star systems that allow such objects to form and survive. Moreover, the cooling process of ultramassive white dwarfs is different. Because of their density and composition, they cool slower or in unique patterns compared to regular white dwarfs. This makes them cosmic clocks that can tell us about the age of certain parts of our galaxy, adding a new tool for astronomers to understand galactic history. Magnetic fields also play a crucial role. Many ultramassive white dwarfs have incredibly strong magnetic fields, millions to billions of times stronger than Earth's. These magnetic fields affect the star's structure and behavior. They can influence how the star loses heat, how it spins, and even how it might explode or collapse. Some researchers think that strong magnetic fields might even support ultramassive white dwarfs against gravitational collapse, allowing them to exist above the traditional Chandrasekhar limit. If true, this rewrites parts of astrophysics textbooks. In addition, magnetic fields create fascinating phenomena. They can cause the surface of the star to have star spots, similar to sunspots but far more extreme, influencing the light we detect from these stars. They might also channel particles around the star in powerful beams, somewhat like a cosmic lighthouse. But the mystery doesn't stop there. One of the biggest questions scientists have is how exactly these ultramassive white dwarfs form. There are a few competing theories. One is that they come from the merger of two smaller white dwarfs in a binary system. When two white dwarfs spiral in toward each other, they can collide and merge, producing a single, heavier white dwarf. Depending on the total mass and conditions, this can result in an ultramassive white dwarf rather than an explosion. These mergers are violent and energetic events, but sometimes they might end in a relatively calm, ultramassive white dwarf instead of a supernova. This could explain why some ultramassive white dwarfs have strange chemical compositions and magnetic fields. They carry the scars of their violent past. Another idea is that certain massive stars lose just enough mass during their giant phases to end their lives as ultramassive white dwarfs instead of collapsing into neutron stars or black holes. This could depend on metallicity, the amount of heavier elements in the star, and other environmental factors. The exact path likely varies, and studying these stars helps scientists learn about the complex dance of stellar birth, life, and death. Understanding ultramassive white dwarfs is also important for the bigger cosmic picture. Their behavior might influence how galaxies evolve, how elements are recycled in space, and how the universe changes over billions of years. Because they are remnants of massive stars, they carry clues about star formation rates and the chemical makeup of the universe. When you think about it, ultramassive white dwarfs are kind of like cosmic fossils, holding information about processes that happened long ago and far away, waiting for us to decode. And this makes them exciting targets for future research missions. As our technology improves, with better telescopes, detectors, and computational power, we will uncover even more about these enigmatic stars. In the meantime, the story of ultramassive white dwarfs reminds us of how much there is still to learn about space. No matter how advanced our knowledge gets, the universe has a way of surprising us, pushing the boundaries of science, and inviting us to explore further. Beyond their formation and basic properties, ultramassive white dwarfs also challenge how we understand stellar stability and the ultimate fate of stars. Typically, stars follow well-mapped paths from birth to death, beginning as clouds of gas, igniting into nuclear fusion, then expanding and shedding layers, before collapsing into compact remnants. But ultramassive white dwarfs live on the edge of this order, occupying a borderline zone between stability and collapse. This borderline nature raises questions about their internal structure. One concept scientists use to model white dwarfs is called degeneracy pressure. This is a quantum mechanical effect where electrons resist being squeezed too tightly. It's what prevents a white dwarf from collapsing under its own gravity. Essentially, electrons push back. But as the star grows more massive and denser, the pressure needed to hold it up grows. For ultramassive white dwarfs, this pressure reaches levels that strain what our current physics predicts. There's speculation that as densities increase, new exotic states of matter might appear inside these stars. For example, electrons could combine with protons to form neutrons in a process called inverse beta decay. This could lead to the star slowly transforming into a neutron star without a dramatic explosion. Alternatively, strange quark matter, an exotic, ultra-dense form of matter, could form inside. These theories are still highly speculative but fascinating because they offer glimpses into physics at conditions impossible to replicate on Earth. Another mystery revolves around rotation. Some ultramassive white dwarfs spin very rapidly. Fast rotation can create centrifugal forces that counterbalance gravity, allowing the star to hold more mass before collapsing. It also changes the star's shape, making it less spherical and more oblate, flattened at the poles. This distortion affects the internal physics and how the star cools and emits light. Magnetic fields and rotation can also interact, causing complex behaviors. For instance, differential rotation, where different layers spin at different speeds, might generate magnetic dynamos, amplifying the star's magnetic field. This can influence how the star emits X-rays and other radiation, providing clues about its internal dynamics. We can also consider the role ultramassive white dwarfs might play in producing some of the most energetic events in the universe: gamma-ray bursts, GRBs. These are intense flashes of gamma radiation lasting from milliseconds to minutes, detected from distant galaxies. The exact origins of many GRBs remain mysterious, but some theories link them to the collapse or merger of compact stars. If ultramassive white dwarfs collapse under certain conditions, they might create events powerful enough to produce GRBs or other high-energy phenomena. In the broader context of cosmology, ultramassive white dwarfs impact how we measure distances and expansion in the universe. Type I supernovae, those powerful explosions that help us understand the accelerating expansion, are traditionally thought to occur when a white dwarf nears the Chandrasekhar limit. But if ultramassive white dwarfs exist and behave differently, this could affect how we calibrate these cosmic standard candles, potentially revising our estimates of the universe's age and fate. Scientists continue to debate these points and design observations and experiments to test hypotheses. Every new ultramassive white dwarf discovered adds a piece to this cosmic puzzle, but also often raises more questions. Looking ahead, the next generation of space telescopes, like the James Webb Space Telescope and future X-ray observatories, promise deeper insights into these mysterious stars. These instruments can observe ultramassive white dwarfs in greater detail, capturing subtle signals from their atmospheres, magnetic fields, and surroundings. Meanwhile, advancements in computational astrophysics allow researchers to simulate the extreme physics inside these stars with higher accuracy. These simulations can test different theories about matter under intense pressure and temperature, shedding light on processes that shape ultramassive white dwarfs. And of course, the hunt for gravitational waves continues. If we detect gravitational signals from ultramassive white dwarf mergers or collapses, it would provide direct evidence about their existence and behavior, opening a new era in understanding these cosmic enigmas. In the grand scheme, ultramassive white dwarfs remind us that space isn't just vast, it's full of surprises. Each discovery not only teaches us about stars but challenges our grasp of fundamental physics. They sit at the frontier between the known and unknown, pushing scientists to expand the boundaries of human knowledge. So when you look up at the stars tonight, remember there are mysterious, dense, ultramassive white dwarfs quietly spinning and glowing, carrying secrets that might one day rewrite what we know about the universe itself. Ultramassive white dwarfs sit at a fascinating crossroads in astrophysics, not only because of their extreme physical characteristics but also due to the clues they offer about the life cycle of stars and the ultimate fate of matter under intense pressure. These stars challenge the neat categories astronomers have traditionally used to classify stellar remnants, and their study helps reveal the diversity and complexity hidden in our universe. One of the most intriguing things about ultramassive white dwarfs is how they push the limits of matter. The densities inside these stars are so high that a teaspoon of their material would weigh tons on Earth. Imagine compressing the mass of the Sun into a volume about the size of our planet. That's the scale we're talking about. This extreme environment tests the laws of physics as we know them, forcing us to reconsider the behavior of electrons, protons, and neutrons under these conditions. Because ultramassive white dwarfs are so dense, they also have incredibly strong gravity at their surface, millions of times stronger than Earth's gravity. This intense gravity affects how light escapes from the star's surface, causing phenomena like gravitational redshift, where light loses energy climbing out of the star's gravity well and appears shifted toward the red end of the spectrum. Measuring this redshift allows scientists to estimate the star's mass and radius with greater precision, offering a window into its structure. Adding to this complexity is the role of the star's chemical composition. Most white dwarfs are primarily made of carbon and oxygen, remnants of the nuclear fusion processes that powered the star during its life. However, ultramassive white dwarfs may have cores rich in heavier elements like neon, magnesium, and even silicon, the byproducts of more massive progenitor stars. This changes the star's internal pressure and cooling rates and can influence its magnetic field and evolution. Speaking of cooling, the temperature of ultramassive white dwarfs tells a detailed story. Unlike normal stars that generate energy through fusion, white dwarfs gradually cool down over billions of years, slowly fading as they radiate away residual heat. Because ultramassive white dwarfs have such dense cores, their cooling processes can be significantly slower or exhibit unique phases where the interior crystallizes, forming a solid core much like the diamond structure. This crystallization releases latent heat, temporarily slowing the cooling and creating a kind of cosmic heartbeat detectable by astronomers. Interestingly, this crystallization phenomenon was confirmed with data from the Gaia spacecraft, which observed a pile-up of white dwarfs at certain temperatures, evidence that many are undergoing this phase transition. In ultramassive white dwarfs, this process is even more pronounced because their higher density raises the crystallization temperature. Studying these stars can therefore help us understand matter's behavior in extreme states, with potential applications extending to materials science and quantum physics. Another captivating aspect is how ultramassive white dwarfs might be involved in rare cosmic explosions known as Type Ia supernovae. These events are crucial to cosmology because their consistent brightness allows scientists to measure cosmic distances. The classic scenario involves a white dwarf in a binary system accreting matter from a companion star until it hits the Chandrasekhar limit and explodes. But ultramassive white dwarfs complicate this picture because their mass may already exceed or approach this limit. Depending on factors like rotation, magnetic fields, and composition, some may avoid exploding and remain stable, while others might collapse or detonate in unexpected ways. This opens a whole field of study about the diversity of supernova mechanisms. Could ultramassive white dwarfs produce new types of explosions or even fail to explode, quietly collapsing into neutron stars? These questions have important implications for understanding the chemical evolution of galaxies, as supernovae are responsible for dispersing heavy elements essential for planet formation and life. In addition, the presence of strong magnetic fields in ultramassive white dwarfs raises questions about how these fields form and evolve. One hypothesis suggests that the magnetic fields could be remnants from the progenitor star, amplified during the collapse phase, or generated through the merging of two white dwarfs. These magnetic fields might influence the star's rotation, surface temperature distribution, and emission of radiation across the electromagnetic spectrum, including X-rays and radio waves. Studying these magnetic effects could also reveal connections to magnet-Rs, neutron stars with extremely powerful magnetic fields, and shed light on the transition processes between white dwarfs and neutron stars. The line between these objects may not be as clear-cut as once thought, especially for ultramassive white dwarfs on the brink of collapse. Recent observations of ultramassive white dwarfs in binary systems provide another exciting avenue. By tracking their orbits and interactions, astronomers can infer details about mass transfer, tidal forces, and eventual fates of these systems. In some cases, the binary companion might be a neutron star or black hole, creating extreme environments for studying gravitational waves and testing Einstein's theories. Speaking of gravitational waves, ultramassive white dwarfs could be sources of these ripples in spacetime if they merge with other compact objects. The Laser Interferometer Space Antenna, LISA, a future space-based gravitational wave detector, is expected to detect signals from white dwarf binaries, helping confirm theoretical models and uncover previously hidden populations of ultramassive white dwarfs. Looking at the bigger picture, ultramassive white dwarfs also provide clues about stellar population dynamics and the chemical evolution of galaxies. By studying their numbers, ages, and distribution in the Milky Way, astronomers can piece together the history of star formation and death in our galaxy, learning how elements cycle through space and seed new generations of stars and planets. There's also a fascinating connection between ultramassive white dwarfs and planetary systems. Some white dwarfs have been found with debris disks or even planets orbiting them. Understanding how these compact stars interact with surrounding material can tell us about the ultimate fate of planetary systems, including what might happen to our own solar system billions of years from now. On a more theoretical level, ultramassive white dwarfs provide a unique laboratory to test fundamental physics. The conditions inside them approach extremes where our current models of particle physics, quantum mechanics, and general relativity intersect. This could lead to discoveries about the behavior of matter under pressures and densities unreachable on Earth. For example, the equation of state, which describes how matter behaves under various pressures and temperatures, can be constrained by studying ultramassive white dwarfs. This helps physicists refine their understanding of dense matter and could have implications for nuclear physics, materials science, and cosmology. Furthermore, by comparing observations with detailed computer simulations, scientists can improve models of stellar evolution, supernova mechanisms, and compact object physics. These improvements have ripple effects across many fields, from predicting cosmic element abundances to interpreting signals from distant galaxies. The more we learn about ultramassive white dwarfs, the clearer it becomes that these stars are not just exotic curiosities but vital pieces in the cosmic puzzle. Their existence challenges simplistic ideas about stellar death and pushes us to explore the full range of possibilities in how stars live and die. Ultramassive white dwarfs are dense, mysterious stars that sit near the limits of what physics currently explains. They offer insights into matter under extreme conditions, star formation and death, and the chemical enrichment of the universe. They may produce unique cosmic explosions or quietly collapse into neutron stars, and their strong magnetic fields and rapid rotation make them laboratories for exotic physics. They are also important for understanding cosmic distances and the expansion of the universe, influencing how we interpret the light from distant supernovae. Observing these stars continues to improve with new technology, promising even deeper insights in the coming decades. Ultramassive white dwarfs remind us that the universe is far from simple. It holds countless mysteries in tiny, dense packages, waiting for us to unravel their secrets. By studying these stars, we not only learn about distant cosmic phenomena but also about the fundamental laws that govern reality itself. Ultramassive white dwarfs stand out as some of the most extreme and enigmatic objects in the universe, and digging deeper into their mysteries reveals just how much they push the boundaries of what we know. Their story doesn't end with their mass or density. In fact, those features only begin to hint at the remarkable physics and cosmic histories wrapped up inside them. One key question scientists wrestle with is how exactly these ultramassive white dwarfs form in the first place. Most white dwarfs come from stars with masses similar to or just a few times greater than our Sun. But ultramassive white dwarfs, which can reach or even exceed 1.3 times the mass of the Sun, are believed to come from stars that started out with 8 to 10 times the Sun's mass. The way these heavier stars shed their outer layers and leave behind such compact remnants involves a complex dance of nuclear burning, stellar winds, and sometimes explosive events. Understanding these processes better will help us grasp not only ultramassive white dwarfs but also how elements are created and dispersed through space. Adding to this complexity, some ultramassive white dwarfs might actually form when two smaller white dwarfs collide and merge. This scenario is still being studied, but if true, it changes how we think about the life cycles of stars and the creation of supernovae. Such mergers might even produce rare and unusual types of supernova explosions, or lead to the direct collapse into neutron stars without any explosive event at all. These merger events aren't just theoretical. They're a hot topic because they could explain certain puzzling observations of supernovae that don't fit into classic models. For example, some type I supernovae are brighter or dimmer than expected, and the merging white dwarf model might clarify these discrepancies. Detecting these mergers and understanding their aftermath will likely be a major focus in astronomy over the coming decades. The role of magnetic fields in ultramassive white dwarfs also continues to intrigue astronomers. Some of these stars have magnetic fields billions of times stronger than Earth's. These fields influence everything from the star's rotation speed to how it cools down and emits radiation. There's evidence that intense magnetic fields can alter the internal structure of these stars, affecting how they transport heat and even delaying or speeding up certain evolutionary processes. Magnetic fields could also explain why some ultramassive white dwarfs spin incredibly fast, sometimes rotating once every few seconds. This rapid spin, combined with extreme gravity and magnetic forces, creates an environment that might accelerate particles to near light speed and produce emissions detectable across many wavelengths, including X-rays and gamma rays. This radiation can help scientists map the magnetic and structural properties of these stars, improving our understanding of their inner workings. Moving beyond individual stars, ultramassive white dwarfs offer clues about the structure and evolution of our galaxy. Since white dwarfs are remnants of stars that lived billions of years ago, studying their distribution and ages allows astronomers to trace back star formation history in different parts of the Milky Way. Patterns in where ultramassive white dwarfs are found might reveal past galactic events like bursts of star formation or interactions with other galaxies. Additionally, white dwarfs in general are used to estimate the age of the oldest stars in the galaxy. Because ultramassive white dwarfs cool at different rates compared to their lighter counterparts, understanding their cooling patterns refines these age estimates, which in turn help us pin down the timeline of the universe's development. The existence of ultramassive white dwarfs also hints at the ultimate fate awaiting many stars, including possibly our Sun's distant descendants. As stars reach the end of their lives, shedding layers and leaving behind dense cores, the processes observed in ultramassive white dwarfs could reflect the future stages of stellar evolution under specific conditions. Knowing these details shapes our understanding of cosmic recycling, how the elements forged in stars become the building blocks of new stars, planets, and eventually life. Surrounding these white dwarfs, astronomers have sometimes detected disks of dust and gas, remnants of destroyed planets or asteroids. This discovery has implications for planetary system evolution and survival in extreme conditions. Studying these disks around ultramassive white dwarfs tells us how planetary bodies fare when their host stars die and shrink into compact objects. It also raises questions about whether planets could exist or form anew around these dense stars. The techniques used to detect and analyze ultramassive white dwarfs are a story in themselves. Because these stars are so faint and small, spotting them requires powerful telescopes and precise instruments capable of measuring subtle changes in light and gravitational effects. Missions like the Gaia spacecraft have revolutionized this field by providing detailed positions, motions, and brightness measurements for millions of stars, including many white dwarfs. Gaia's data helped astronomers identify an unexpected population of ultramassive white dwarfs, allowing for statistical studies that were impossible before. With this treasure trove of data, researchers can explore patterns, test models of star evolution, and refine estimates of the physical properties of these stars. Future missions and ground-based observatories will continue to expand our knowledge, perhaps discovering even more exotic objects or phenomena related to ultramassive white dwarfs. Theoretical models and computer simulations are also crucial in this research. By modeling the physics inside ultramassive white dwarfs, accounting for factors like electron degeneracy pressure, nuclear fusion remnants, and relativistic effects, scientists can predict how these stars behave, cool, and possibly explode. Comparing simulations with observations helps validate or challenge these models, driving improvements and uncovering gaps in our understanding. Another important question involves the stability of ultramassive white dwarfs. According to classic theory, the Chandrasekhar limit marks the maximum mass a white dwarf can have before collapsing under its own gravity. Ultramassive white dwarfs skirt this limit, and in some cases appear to exceed it. How do they remain stable? Possible explanations include rapid rotation, which generates centrifugal force counteracting gravity, or strong magnetic fields providing additional support. If these stars do collapse, they might turn into neutron stars or trigger supernova explosions, both of which profoundly impact their surroundings. Such events seed space with heavy elements and influence star formation in nearby regions. They also produce phenomena like pulsars and black holes, adding complexity to cosmic evolution. The study of ultramassive white dwarfs also links to fundamental physics problems. For example, how matter behaves at nuclear densities is still not fully understood, and these stars provide natural laboratories for such extreme conditions. Questions about particle interactions, quantum states, and relativistic physics arise naturally when probing their interiors. In recent years, researchers have proposed that ultramassive white dwarfs might help explain dark matter or other cosmic mysteries. While speculative, these ideas show how investigating these stars can intersect with the biggest questions in astrophysics and cosmology. From a broader viewpoint, ultramassive white dwarfs remind us how the universe operates on scales and conditions far beyond everyday experience. These dense stars are tiny beacons of extreme physics, formed from the life and death of massive stars, yet influencing galaxies and cosmic cycles. The search for new ultramassive white dwarfs and the detailed study of known ones will continue to push forward, fueled by new telescopes, computational power, and theoretical breakthroughs. The next decades promise exciting discoveries, as we learn more about these cosmic heavyweights, their origins, behaviors, and ultimate destinies. In essence, ultramassive white dwarfs are more than just heavy stars. They are keys to unlocking the mysteries of matter, energy, and evolution on the grandest scales. Their study touches on the very fabric of the cosmos, connecting nuclear physics, stellar evolution, galactic history, and the fate of the universe itself. Digging even deeper, one fascinating aspect about ultramassive white dwarfs is the question of their composition. While most typical white dwarfs are primarily made of carbon and oxygen, ultramassive ones often have cores dominated by oxygen, neon, and sometimes even magnesium. This shift in elemental makeup comes from the progenitor stars being more massive, which means their cores undergo more advanced nuclear burning stages before collapsing into white dwarfs. This difference in composition affects everything, from their density and structure to how they cool down over billions of years. The process of nuclear burning inside stars that eventually become ultramassive white dwarfs involves fusing heavier elements after carbon and oxygen, such as neon and magnesium. These elements are produced in the late stages of stellar evolution for stars more massive than about 8 times the mass of the Sun. When the star exhausts its nuclear fuel, it can't generate enough pressure to fight gravity, and the outer layers get blown away, leaving behind this dense core rich in heavier elements. What's wild is that these heavier elements inside ultramassive white dwarfs influence their thermal evolution. Since neon and magnesium have different nuclear properties and heat capacities compared to carbon and oxygen, they change how heat flows inside the star. This, in turn, affects the cooling rate, how fast a white dwarf dims and fades over billions of years. By observing the cooling of ultramassive white dwarfs, astronomers can test these theoretical models, comparing what they see in the sky with what physics predicts. Another intriguing feature is that ultramassive white dwarfs seem to cool slower than lighter white dwarfs. This slower cooling can make them appear brighter for longer periods, which is a clue to their internal physics. Their dense interiors might trap heat more effectively, or the crystallization process, the transition of the star's core from a fluid to a solid, might release energy that keeps the star warmer for extended times. Crystallization in white dwarfs is a bit like the freezing of water into ice, but under mind-boggling pressures millions of times higher than Earth's surface. This crystallization doesn't just affect cooling, it can also impact the star's structure and evolution. In ultramassive white dwarfs, the crystallization front moves through the core, changing its mechanical properties and potentially influencing the star's rotation and magnetic field distribution. The details of this process are still being studied, but it's a perfect example of how ultramassive white dwarfs are living laboratories for exotic physics. Let's talk about rotation for a moment. We know that many stars spin, and when a star collapses into a white dwarf, conservation of angular momentum usually makes it spin faster, sort of like an ice skater pulling in their arms. Some ultramassive white dwarfs spin incredibly rapidly, making a full rotation in seconds or minutes. This rapid spin has major implications for their stability. If they spin fast enough, centrifugal force can counteract the crushing gravity, allowing the white dwarf to exceed the classical Chandrasekhar limit, which is about 1.4 times the mass of the Sun. This spin-driven support might explain why some ultramassive white dwarfs don't collapse into neutron stars or explode as supernovae despite their extreme masses. However, it's a delicate balance. As the star loses energy and slows down over time, due to magnetic braking or radiation, it might eventually reach a tipping point and collapse. This slowdown and eventual collapse process could be linked to rare but extremely powerful cosmic explosions. One real-world connection to this is a type of supernova called Type I. These supernovae happen when a white dwarf in a binary system accumulates material from a companion star until it reaches the Chandrasekhar limit and explodes. But some Type I supernovae seem to come from progenitors more massive than this limit, hinting that ultramassive, rapidly spinning white dwarfs could be behind these events. This theory helps explain variations in brightness and behavior among Type I supernovae. Ultramassive white dwarfs also provide a window into the strong magnetic fields seen in some stars. Some of these stars have magnetic fields exceeding 1 billion times Earth's, the strongest known outside of neutron stars and black holes. The origins of such intense fields are still debated. One idea is that magnetic fields get amplified during the star's collapse phase or through mergers with other white dwarfs. These magnetic fields affect the star's atmosphere and can create spots or regions where the magnetic force suppresses convection, the movement of hot material. This changes the surface temperature distribution, producing variations in brightness that astronomers can observe. Studying these patterns gives clues about how magnetic fields shape the star's behavior and evolution. An especially fascinating mystery is whether ultramassive white dwarfs could be related to some of the universe's most enigmatic phenomena, like fast radio bursts, FRBs. FRBs are extremely brief, intense bursts of radio waves from distant galaxies. Some theories propose that magnetized white dwarfs, including ultramassive ones, might be sources of these bursts, either through star quakes or interactions with surrounding material. Looking at the bigger picture, ultramassive white dwarfs help us understand galactic chemical evolution. Since they contain heavier elements like neon and magnesium, when these stars eventually end their lives, whether through collapse or other means, they return these elements to space, enriching the interstellar medium. This process seeds future generations of stars and planets with the ingredients needed for complex chemistry and potentially life. Another link to planetary systems is the presence of debris disks around some ultramassive white dwarfs. These disks are made of dust and gas from disrupted asteroids or planets, remnants of a planetary system's violent past. Detecting these disks helps us understand what happens to planets when their host stars die and shrink to white dwarfs. It's a cosmic glimpse into the fate of planetary systems, including possibly our own solar system in the far future. When it comes to detecting these stars, technology plays a huge role. The European Space Agency's Gaia mission revolutionized white dwarf astronomy by measuring distances, motions, and brightness from millions of stars. This data helped identify many ultramassive white dwarfs, allowing researchers to study their properties in unprecedented detail. Beyond Gaia, upcoming telescopes like the James Webb Space Telescope and future ground-based observatories will give even sharper views, especially in infrared and other wavelengths. These instruments will let scientists peer into the atmospheres and surroundings of ultramassive white dwarfs, probing their composition, temperature, magnetic fields, and more. Numerical simulations and modeling are also vital. By simulating the physics inside ultramassive white dwarfs, including electron degeneracy pressure, magnetic field effects, and rotation, scientists can predict what these stars should look like and how they behave. Comparing these predictions with observations sharpens our understanding and helps uncover new physics. The study of ultramassive white dwarfs also touches on fundamental physics questions, like how matter behaves under extreme density and pressure. Inside these stars, electrons are squeezed so tightly they exhibit quantum behaviors unseen on Earth. These conditions test our theories of matter and forces, making ultramassive white dwarfs natural physics labs. Some theorists have even suggested ultramassive white dwarfs might hold clues about dark matter. Although speculative, these ideas show how studying these stars can connect with the biggest mysteries of cosmology. Another remarkable feature is the link between ultramassive white dwarfs and the overall life cycle of stars in our galaxy. Since white dwarfs are remnants of dead stars, their population and properties reveal clues about star formation rates, the mass distribution of stars, and the history of the Milky Way. Studying ultramassive white dwarfs helps refine models of stellar evolution, which then impacts our understanding of everything from galaxy formation to the origin of elements essential for life. In short, ultramassive white dwarfs are much more than just heavy, dense stars. They are windows into extreme physics, cosmic evolution, and the fundamental processes shaping our universe. Their mysteries are tightly connected to how stars live and die, how elements form and spread, and how the universe evolves on grand scales. Their study is ongoing and will only grow with new data and insights, promising exciting discoveries for years to come. It's important to highlight that ultramassive white dwarfs also challenge some long-standing assumptions in astrophysics. For example, the classical Chandrasekhar limit, about 1.4 times the Sun's mass, was once thought to be an unbreakable ceiling for white dwarfs. But observations of these ultramassive white dwarfs suggest that under certain conditions, like rapid rotation or strong magnetic fields, this limit can be surpassed. This realization forces scientists to rethink how stars evolve and die, shaking up decades of textbook astrophysics. This breaking of the Chandrasekhar limit also feeds into the search for the progenitors of peculiar supernovae, the explosions that outshine entire galaxies for weeks or months. Some supernovae appear too bright, or show unusual chemical signatures that don't fit with the standard model of a white dwarf exploding at the classic limit. Ultramassive white dwarfs might be responsible for these outliers, making them central to solving one of the biggest puzzles in stellar death. Beyond these extreme events, ultramassive white dwarfs serve as precise cosmic clocks. Because white dwarfs cool predictably over time, astronomers can estimate their age by measuring their temperature and luminosity. Ultramassive white dwarfs cool differently from normal ones, so understanding them improves age estimates not just for these stars but for the star clusters and galaxies they reside in. This helps paint a clearer picture of the timeline of cosmic history. Delving deeper into the internal structure, the physics governing ultramassive white dwarfs involves the interplay between gravity and electron degeneracy pressure. Electron degeneracy pressure is a quantum mechanical effect where electrons resist being squeezed into the same space. This pressure supports the star against collapsing under its own gravity. However, as the star's mass grows, gravity becomes stronger, pushing electrons to near light speeds, which complicates the pressure balance. At these extreme densities, exotic physics kicks in. For example, the electrons become relativistic, meaning their speeds approach the speed of light, altering the pressure they exert. These relativistic effects limit how massive a white dwarf can be before gravity wins, causing collapse. The existence of ultramassive white dwarfs close to this threshold tests our understanding of relativistic quantum mechanics in astrophysical settings. Another curious topic is the magnetic fields in ultramassive white dwarfs. Some of these stars exhibit magnetic fields billions of times stronger than Earth's. Such immense fields might arise from dynamo processes inside the star or from the merging of two white dwarfs, which can twist and amplify magnetic fields dramatically. These magnetic fields can affect the star's shape, sometimes making it oblate or distorted, and can influence how the star loses energy and cools. Magnetic fields also impact the star's surroundings. For instance, they can channel matter falling onto the white dwarf and binary systems, creating hotspots that emit X-rays or other radiation. Studying these emissions helps astronomers understand how magnetic fields interact with accretion processes and influence the star's evolution. Speaking of binaries, ultramassive white dwarfs often exist in binary star systems. This pairing is crucial because it sets the stage for potential mergers or accretion events that might push the white dwarf over the stability limit. When two white dwarfs merge, the combined mass can exceed the Chandrasekhar limit, possibly triggering a supernova or collapse into a neutron star. The dynamics of such mergers are complex and a hot topic in astrophysics. These merger events also tie into gravitational wave astronomy. As two white dwarfs spiral closer together, they emit gravitational waves, ripples in spacetime predicted by Einstein's theory of relativity. Detecting these waves provides a new way to study ultramassive white dwarfs and their fate, opening a whole new window into stellar evolution. Another fascinating area is the link between ultramassive white dwarfs and neutron stars. If an ultramassive white dwarf collapses, it may form a neutron star, a much denser object made mostly of neutrons. Neutron stars exhibit even more extreme physics, including superfluid interiors and intense magnetic fields. Understanding the conditions under which a white dwarf collapses helps clarify the birth of neutron stars and the diversity of compact objects in the universe. Some ultramassive white dwarfs might also serve as precursors to rare cosmic phenomena called magnetars. Magnetars are neutron stars with ultra-strong magnetic fields, among the most powerful in the cosmos. If an ultramassive white dwarf collapses while retaining a strong magnetic field, it could seed the formation of a magnetar, linking these mysterious stars to even stranger cosmic beasts. We should also consider the chemical evolution that ultramassive white dwarfs contribute to. When these stars eventually shed material, whether through winds, nova eruptions, or catastrophic explosions, they release heavy elements like neon and magnesium into space. These elements enrich the interstellar medium, contributing to the chemical makeup of future stars, planets, and possibly life. Ultramassive white dwarfs also help us understand the fate of our own sun and solar system billions of years from now. Although our sun won't become ultramassive, the processes involved in white dwarf formation and evolution reflect the ultimate destiny of many stars. Studying ultramassive white dwarfs offers a glimpse into how stellar remnants might interact with any surviving planets or debris. Additionally, these stars serve as testbeds for exotic states of matter. Inside their cores, conditions may allow for phases like superionic ice or crystalline lattices of ions, states of matter rarely found outside extreme astrophysical environments. Understanding these phases informs not just astronomy but condensed matter physics and materials science. The role of ultramassive white dwarfs in galactic archaeology cannot be overstated. By studying their properties, astronomers piece together the history of star formation, stellar death, and element distribution in galaxies. This information helps reconstruct how galaxies like the Milky Way formed and evolved over billions of years. Technology continues to revolutionize our understanding. Surveys like Gaia, the upcoming Vera C, Rubin Observatory, and space telescopes provide ever more detailed data, helping find more ultramassive white dwarfs and measure their properties with precision. The synergy of observational data and theoretical modeling pushes the boundaries of what we know. Simulations play a key role, too. High-performance computers simulate the physics of ultramassive white dwarfs, exploring scenarios of mergers, magnetic field generation, cooling, and collapse. These virtual experiments help interpret observations and predict new phenomena to look for in space. Looking ahead, one of the biggest questions is, what happens when an ultramassive white dwarf finally crosses the edge? Does it explode, collapse, or transform in some unexpected way? Understanding this final act ties into fundamental physics, astrophysics, and cosmology. Ultramassive white dwarfs are remarkable cosmic objects packed with mysteries. They challenge theories, reveal extreme physics, and connect with some of the most energetic and enigmatic phenomena in the universe. Their study is a gateway to understanding the life cycle of stars, the behavior of matter under unimaginable conditions, and the dynamic evolution of galaxies. This ongoing journey of discovery promises to reshape our understanding of the cosmos and our place within it. Every new observation and theory brings us closer to unlocking the secrets held within these dense, magnetic, spinning remnants of dead stars. Ultramassive white dwarfs don't just stretch the limits of size and density. They also open up fascinating questions about the balance between matter and energy in the universe. At the heart of these stars, the pressure from electrons squeezed to near light speed battles against gravity's pull, trying to crush the star even further. This battle is what allows the star to survive, but the edge they hover near pushes the boundaries of our understanding of physics. In fact, studying these objects might one day help physicists uncover new principles of quantum mechanics or gravity that we haven't yet discovered. One intriguing idea about ultramassive white dwarfs is their role in the production of Type Ia supernovae. These are critical cosmic events because they serve as standard candles, objects whose brightness we understand well enough to use as measuring sticks for the scale of the universe. Some ultramassive white dwarfs might explode in a different way than the usual Type Ia supernovae, creating variations that could affect how we measure cosmic distances. This has huge implications for understanding the expansion of the universe and the mysterious force we call dark energy. The chemistry of ultramassive white dwarfs also provides clues to their origin. Unlike smaller white dwarfs mostly made of carbon and oxygen, many ultramassive white dwarfs contain cores rich in oxygen, neon, and magnesium. This difference points to a different evolutionary path, usually from more massive progenitor stars that burned heavier elements before collapsing. Studying this chemistry helps astronomers trace the life story of these stars from birth through their complex deaths. Rotation is another fascinating factor in ultramassive white dwarfs. Because these stars are incredibly dense, even a slight spin can have enormous effects on their structure and stability. Rapid rotation can add extra support against gravity, allowing a star to be heavier than the traditional Chandrasekhar limit. This rotation also influences how the star cools and emits radiation, which affects what we see when we observe them through telescopes. Magnetic fields, combined with rotation, create some of the most exotic environments in the universe. Some ultramassive white dwarfs have magnetic fields trillions of times stronger than Earth's, enough to affect the star's atmosphere and how particles move around it. These fields can trap charged particles, creating auroras and hotspots that produce X-rays and other energetic emissions detectable by space observatories. Ultramassive white dwarfs also have a role in binary star systems. When paired with another star, these dense remnants can pull matter from their companion, causing dramatic outbursts known as novae. In some cases, the mass transfer can push the white dwarf over its stability limit, leading to catastrophic events like supernovae. Understanding these processes is crucial because they contribute to the chemical enrichment of the galaxy and affect the life cycle of stars. The discovery of ultramassive white dwarfs also challenges the neat categories astronomers once used to classify stars and stellar remnants. These stars don't fit perfectly into existing models, hinting at new classes of objects or transitions between known types, like the boundary between white dwarfs and neutron stars. This gray area is a playground for astrophysicists seeking to refine theories of stellar evolution. Cooling rates of ultramassive white dwarfs offer another rich source of information. These stars cool more slowly than their lighter counterparts due to their dense cores and unique chemical compositions. By measuring their temperatures and luminosities, scientists can estimate their ages and thereby date the star populations of the Milky Way, providing insight into the galaxy's history. From a technological perspective, advancements in telescopes and detectors are revolutionizing our ability to study ultramassive white dwarfs. Space-based observatories like the Hubble Space Telescope, the Chandra X-ray Observatory, and the Gaia mission have vastly expanded our catalog of these stars and improved measurements of their properties. Future missions promise even more detailed observations, opening windows into these mysterious stellar remnants. Astrophysicists also use computer simulations to model the extreme conditions inside ultramassive white dwarfs. These simulations incorporate physics at atomic, nuclear, and quantum levels to predict how these stars behave and evolve. By comparing simulation results with actual observations, scientists can test their theories and refine models of stellar structure. The ultimate fate of ultramassive white dwarfs is still an open question, adding to their mystery. Depending on factors like mass, rotation, and magnetic field strength, they might explode as supernovae, collapse into neutron stars, or possibly form exotic states of matter. Each outcome has significant consequences for the surrounding space environment and the broader cosmos. Some researchers speculate that ultramassive white dwarfs could be involved in forming black holes, though this is less certain. If a white dwarf collapses beyond the neutron star stage, it could cross the event horizon and become a black hole. While rare, such a transition would mark an extraordinary endpoint in the life cycle of a star. Ultramassive white dwarfs also inform studies of gravitational waves, ripples in space-time caused by massive objects accelerating or colliding. When two white dwarfs merge, they produce gravitational waves detectable by instruments like LIGO and Virgo. These signals help scientists learn about the properties of ultramassive white dwarfs and the physics of their mergers. This connection between ultramassive white dwarfs and gravitational waves is one of the most exciting frontiers in modern astronomy. It offers a new way to listen to the universe and understand events that would otherwise remain invisible or poorly understood. The study of ultramassive white dwarfs intersects with other cosmic mysteries, like dark matter and dark energy. Although not directly related, understanding the behavior of matter at extreme densities and energies might shed light on these fundamental but elusive components of the universe. On a more philosophical note, ultramassive white dwarfs remind us of the universe's complexity and the limits of human knowledge. They represent extreme conditions that test the laws of physics and challenge our understanding, highlighting how much remains to be discovered beyond our current theories. The story of ultramassive white dwarfs is a testament to human curiosity and ingenuity. From the early days of astronomy to today's sophisticated space missions and computational models, these stars have pushed scientists to develop new tools, ideas, and collaborations across disciplines. As we continue to explore the cosmos, ultramassive white dwarfs will remain key to unlocking the secrets of stellar death, cosmic evolution, and the fundamental forces shaping the universe. Each discovery brings us closer to answering profound questions about our origins and the nature of reality itself. One fascinating aspect of ultramassive white dwarfs is their sheer density. Imagine packing the mass of the Sun into a volume roughly the size of Earth. This is a typical white dwarf, but ultramassive ones go even further. Their densities can reach millions of times that of water, meaning a teaspoon of white dwarf matter would weigh tons on Earth. This extreme compactness results from the gravitational collapse of the star after it has exhausted its nuclear fuel, and the pressure that resists further collapse is not from heat or fusion but from the quantum mechanical principle called electron degeneracy pressure. Electron degeneracy pressure comes from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. When a star collapses, electrons are squeezed so tightly that this principle creates a powerful pressure pushing back against gravity. However, this force has a limit. Beyond about 1.4 times the mass of our Sun, a value known as the Chandrasekhar limit, electron degeneracy pressure can no longer support the star, and the star collapses further into a neutron star or black hole. Ultramassive white dwarfs are fascinating because some have masses very close to or exceeding this limit, forcing astronomers to rethink or refine this boundary. Scientists have debated how ultramassive white dwarfs manage to exist with masses that seem to break traditional rules. One explanation involves the effects of strong magnetic fields. These fields can provide additional pressure that helps support the star against collapse. Another explanation includes rapid rotation, which creates centrifugal force that counteracts gravity. Both these factors combined could push the limits of mass a white dwarf can hold before collapsing. This reveals just how dynamic and complex these stellar remnants can be. The origins of ultramassive white dwarfs often involve stars that started with more than 8 times the mass of our Sun. Such massive stars don't simply evolve into ordinary white dwarfs. Instead, they burn heavier elements in their cores, moving past carbon and oxygen to neon and magnesium. Eventually, they shed their outer layers and leave behind a dense core that can exceed the typical white dwarf mass. Some ultramassive white dwarfs may also form through the merging of 2 smaller white dwarfs in binary star systems, creating a single more massive star. These mergers are violent and energetic processes that could also lead to rare types of supernovae. The process may not only create ultramassive white dwarfs but sometimes trigger explosions that spread heavy elements across the galaxy. Such explosions are critical for distributing the building blocks of planets and life throughout the universe. The elements heavier than iron, which are vital for rocky planets and life as we know it, are believed to be produced in part through these supernova events. Observing ultramassive white dwarfs is challenging because their small size and faint light make them difficult targets. However, thanks to improvements in technology like the Gaia Space Telescope, astronomers are discovering more of these objects than ever before. Gaia's precise measurements of star positions, distances, and motions help identify white dwarfs by separating them from other types of stars. This allows researchers to build more complete catalogs and understand their distribution in our galaxy. The study of ultramassive white dwarfs also contributes to our knowledge of stellar populations and the evolution of the Milky Way. By knowing where these stars are in their ages, astronomers can piece together how star formation and death have shaped our galaxy over billions of years. The oldest white dwarfs give clues about the early history of the Milky Way, while younger ones trace more recent star formation. Another exciting discovery related to ultramassive white dwarfs is the existence of crystallized cores. When the temperature inside a white dwarf drops low enough, the ions inside start to form a crystal lattice, essentially turning the core into a giant diamond-like structure. For ultramassive white dwarfs, this crystallization process begins earlier and plays a significant role in their cooling and evolution. This idea was confirmed with data from the Kepler Space Telescope, which observed brightness variations consistent with crystallization effects. This crystallization process slows down the cooling of the star, making it appear brighter and younger than it actually is. This complicates the determination of the star's age, but also provides a new window into studying the physics of matter under extreme conditions. Such insights have implications not only for astrophysics but also for materials science and fundamental physics. Understanding the temperature and cooling rate of ultramassive white dwarfs is crucial because these factors impact how long they remain visible to telescopes. White dwarfs cool over billions of years, and ultramassive ones cool more slowly, so they remain luminous for longer. This makes them useful as cosmic clocks for estimating the age of star clusters and even the age of the galaxy itself. The behavior of ultramassive white dwarfs in binary systems is another rich field of study. When paired with a companion star, the white dwarf can pull gas from its partner. This gas forms an accretion disk around the white dwarf, heating up as it spirals inward and causing the system to emit bright X-rays and ultraviolet light. These interactions can lead to phenomena like novae, explosive flashes caused by the sudden ignition of hydrogen on the white dwarf's surface. If the mass transfer continues and pushes the white dwarf beyond its stability threshold, it may explode as a supernova. Studying these binary systems helps astronomers understand the processes leading to some of the most energetic events in the universe. It also explains how elements critical to life and planets get dispersed into space. Ultramassive white dwarfs are also linked to the field of gravitational wave astronomy. When two white dwarfs orbit each other closely, they emit gravitational waves, ripples in the fabric of spacetime predicted by Einstein's theory of general relativity. Instruments like LIGO and Virgo have begun detecting gravitational waves from mergers of compact objects, providing new ways to study ultramassive white dwarfs indirectly. The detection of gravitational waves from white dwarf mergers opens up a new window into understanding the final stages of these stars. It complements traditional electromagnetic observations and allows scientists to test theories about the structure and evolution of white dwarfs, especially at their most extreme masses. Magnetic fields in ultramassive white dwarfs may also be linked to the generation of high-energy phenomena such as magnetars, neutron stars with incredibly strong magnetic fields. While ultramassive white dwarfs themselves are not magnetars, their evolution and collapse might form magnetars in some cases, connecting these exotic objects through stellar evolution pathways. Another layer of mystery surrounds the role of ultramassive white dwarfs in chemical evolution. Because they form from massive stars that have gone through advanced stages of nuclear fusion, they contain different proportions of elements compared to regular white dwarfs. These compositions affect the types of elements they release during supernova explosions, shaping the chemical makeup of future star systems and planets. Looking ahead, upcoming space missions and telescopes promise to revolutionize our understanding of ultramassive white dwarfs. The James Webb Space Telescope, with its powerful infrared capabilities, will be able to study cooler and more distant white dwarfs, revealing more about their properties and distributions. New ground-based telescopes like the Extremely Large Telescope will also contribute with unprecedented resolution and sensitivity. These advances will help answer many open questions. How exactly do ultramassive white dwarfs form? What physical processes govern their structure and stability? What role do they play in the life cycle of stars and the enrichment of the cosmos? And how might they challenge or confirm our understanding of fundamental physics? The study of ultramassive white dwarfs illustrates the broader story of astronomy. Each discovery raises new questions, pushing the boundaries of what we know and inspiring deeper curiosity about the universe. They remind us that the cosmos is full of wonders waiting to be explored, often in the smallest and densest places imaginable. The quest to understand these stars is also a testament to human creativity and persistence. It involves international collaborations, decades of observations, and the use of cutting-edge technology, all united by the desire to grasp the nature of matter, energy, and cosmic evolution. Ultramassive white dwarfs, though faint and distant, shine a bright light on some of the biggest mysteries in science. They connect the tiniest quantum effects to the vast scales of galaxies, weaving a complex story about the forces shaping the universe. As we keep studying these objects, we not only learn about stars but also about the origins of the elements, the fate of our own sun, and the cosmic cycle of birth and death that underlies existence itself. Every new ultramassive white dwarf discovered adds a piece to this cosmic puzzle, revealing the remarkable extremes of nature and the incredible power of human inquiry. The story of ultramassive white dwarfs is far from over. It continues to unfold with every observation, every theory, and every mission aimed at unlocking the secrets held in the densest corners of space. Ultramassive white dwarfs challenge what we thought we knew about the ultimate fate of stars. Traditional models predicted a pretty neat division between stars that end up as white dwarfs and those that collapse into neutron stars or black holes, but ultramassive white dwarfs blur that line. They exist in this strange gray area, pushing the limits of physics and forcing astronomers to rethink stellar evolution pathways. For example, the exact processes that allow a star to stop collapsing and remain stable at these masses remain a topic of intense research and debate. One of the intriguing puzzles is how these ultramassive white dwarfs avoid collapsing into neutron stars or triggering a supernova prematurely. It seems that strong internal magnetic fields and rapid rotation may provide additional support to counteract gravity. However, measuring these fields is incredibly difficult, and much of the evidence comes from indirect observations or theoretical modeling. The strength and configuration of magnetic fields in ultramassive white dwarfs are active areas of study, with new data gradually filling in the gaps. Another factor scientists consider is the composition of these stars. Many ultramassive white dwarfs have cores rich in heavier elements like neon and magnesium, rather than the usual carbon and oxygen found in lighter white dwarfs. This difference affects how the star behaves under extreme pressures and temperatures. It also influences how these stars cool over time, and how they react to accreting matter from a companion star in binary systems. Understanding cooling rates is crucial because white dwarfs serve as cosmic chronometers. The time it takes for a white dwarf to cool to a certain temperature reveals its age, which in turn helps astronomers determine the age of the star cluster or region it inhabits. But in ultramassive white dwarfs, phenomena like crystallization and magnetic field effects complicate these calculations. Crystallization, where the core forms a solid lattice, releases latent heat, slowing cooling and making the star appear younger than it is. This means the clocks astronomers use to date parts of our galaxy need careful recalibration when ultramassive white dwarfs are involved. It's a reminder of how interconnected these cosmic processes are. Tiny shifts in atomic behavior can ripple outward, affecting galactic-scale measurements. Beyond the physics, ultramassive white dwarfs also play a role in enriching the universe with elements necessary for planets and life. When these stars explode as supernovae, they spew out heavy elements into space. These explosions can seed future star systems with materials like iron, calcium, and other metals essential for building rocky planets and supporting complex chemistry. Astronomers have long sought to understand which types of supernovae come from white dwarfs reaching critical mass, and which come from massive stars collapsing directly. The role of ultramassive white dwarfs in this landscape is critical because they straddle the boundary and could produce unique types of supernovae that differ in brightness and element production. These distinctions matter because supernovae also serve as distance markers in the universe. By studying their brightness and frequency, scientists measure the expansion rate of the universe and explore dark energy, the mysterious force driving cosmic acceleration. Thus, ultramassive white dwarfs indirectly help us map the universe's large-scale structure. In recent years, the detection of gravitational waves has opened a completely new window into understanding ultramassive white dwarfs and their role in cosmic events. When two white dwarfs in a binary system spiral together and merge, they emit gravitational waves, ripples in spacetime that instruments like LIGO and Virgo can detect. These mergers can produce ultramassive white dwarfs or lead to supernova explosions if the combined mass exceeds stability limits. Detecting these signals not only confirms theoretical models but also offers clues about the frequency and outcomes of such mergers. This new observational technique complements traditional telescopes, providing a fuller picture of stellar death and rebirth. Additionally, the violent environments around some ultramassive white dwarfs lead to fascinating phenomena like novae and dwarf novae, temporary brightening events caused by sudden ignition of accumulated gas on the star's surface. These outbursts give astronomers clues about the star's environment, accretion processes, and magnetic fields. Studying the light emitted during these events across different wavelengths, optical, ultraviolet, X-ray, helps reveal details about the physical conditions near the white dwarf. Each eruption is like a natural laboratory for extreme physics. Astronomers also examine pulsations in white dwarfs, small periodic brightness variations caused by internal vibrations. These pulsations provide insights into the star's interior structure, composition, and cooling processes. In ultramassive white dwarfs, these pulsations are especially valuable because they reveal how dense matter behaves under extreme pressures. Another fascinating topic is the fate of our own Sun. While the Sun is not massive enough to become an ultramassive white dwarf, understanding these extreme objects helps us place our star's future in context. The Sun will eventually become a typical white dwarf, but by studying ultramassive ones, scientists can understand the full range of possible endpoints for stars of different sizes. The discoveries made studying ultramassive white dwarfs also influence broader physics questions. For example, they test our understanding of matter at densities that can't be replicated on Earth. They also serve as natural laboratories for testing quantum mechanics, general relativity, and nuclear physics. The pressure and density inside an ultramassive white dwarf compress atoms into a state where electrons are forced into their lowest energy states, creating a sea of degenerate matter. This matter behaves in ways very different from everyday materials, offering clues to how matter might behave in neutron stars or even inside black holes. One open question is whether any white dwarfs could exist above the traditional Chandrasekhar limit under certain conditions, such as rapid rotation or magnetic support. If so, this would revise our understanding of stellar physics and the life cycle of stars. Astronomers are also exploring the connection between ultramassive white dwarfs and mysterious cosmic phenomena such as fast radio bursts, FRBs, and soft gamma-ray repeaters, SGRs. While these events are typically linked to neutron stars or black holes, some theories suggest that ultramassive white dwarfs with strong magnetic fields could also be sources. The possibility that ultramassive white dwarfs could produce or contribute to such high-energy phenomena is an exciting frontier, combining astrophysics with high-energy particle physics and magnetohydrodynamics. As technology advances, we can expect more discoveries that challenge and refine our understanding. Instruments like the European Space Agency's upcoming Plato mission and future gravitational wave detectors will provide more precise data about white dwarfs' properties and behaviors. Meanwhile, computer simulations are becoming ever more sophisticated, modeling the complex interplay of gravity, quantum mechanics, magnetic fields, and nuclear physics inside these stars. These simulations guide observations and help interpret data. Overall, ultramassive white dwarfs stand at the crossroads of many scientific fields. They illuminate the life and death of stars, the origins of elements, and the fundamental laws of physics. Their study is a journey into extremes, from unimaginably dense matter to powerful magnetic fields and explosive cosmic events. In this journey, each discovery leads to new questions and a deeper appreciation of the universe's complexity. Ultramassive white dwarfs may be small in size but are colossal in what they reveal about the cosmos. Ultramassive white dwarfs are also pivotal in shaping our understanding of galactic evolution. Because these stars are the remnants of some of the most massive progenitors that still end their lives as white dwarfs, their distribution, ages, and compositions offer astronomers clues about the history and development of the Milky Way and other galaxies. By surveying the populations of ultramassive white dwarfs across different parts of a galaxy, researchers can infer patterns of star formation and the chemical enrichment of the interstellar medium over billions of years. One challenge in studying ultramassive white dwarfs is their relative rarity. They are far less common than typical white dwarfs, largely because stars massive enough to produce them but not massive enough to collapse into neutron stars occupy a narrow initial mass range. This rarity means that large, detailed samples of ultramassive white dwarfs are hard to assemble, limiting statistical studies. However, with improvements in telescope sensitivity and survey coverage, astronomers are steadily identifying more candidates. Space missions like the Gaia Observatory have been revolutionary in this regard. Gaia's precise measurements of stellar positions, distances, and motions help identify white dwarfs across the galaxy and determine their masses with better accuracy. By measuring a star's parallax, Gaia provides accurate distance data, which, combined with brightness and temperature information, allows astronomers to calculate the star's size and mass more precisely. These refined measurements have revealed several ultramassive white dwarfs previously hidden among the broader population, confirming that they exist in greater numbers than once believed. This influx of data is reshaping models of stellar evolution and white dwarf cooling. The chemical composition of ultramassive white dwarfs' atmospheres is another window into their past. White dwarfs generally have atmospheres dominated by hydrogen or helium, but in some cases, heavier elements are detected. These metals often come from accretion of material from companion stars or from disrupted asteroids and comets. The presence of metals in ultramassive white dwarf atmospheres can reveal details about their environment and history of mass transfer. In binary systems, the interaction between an ultramassive white dwarf and its companion star can lead to dramatic phenomena. For instance, if the white dwarf accumulates enough material from its partner, it can approach or exceed the Chandrasekhar limit, potentially triggering a Type I supernova explosion. These explosions are crucial for cosmic distance measurement and chemical enrichment, but still hold mysteries regarding their exact triggering mechanisms. The stability of ultramassive white dwarfs under such accretion conditions depends heavily on internal physics, including temperature, magnetic fields, and rotation. Some ultramassive white dwarfs might even avoid explosion, instead collapsing quietly into neutron stars or forming exotic objects like magnetars with extraordinarily strong magnetic fields. Magnetars are a class of neutron stars with magnetic fields trillions of times stronger than Earth's, and some theories propose that highly magnetized ultramassive white dwarfs could be progenitors to these extreme stars. This connection between ultramassive white dwarfs and neutron stars bridges key gaps in understanding how the most magnetic and compact objects in the universe form. Additionally, the discovery of pulsating ultramassive white dwarfs, stars that rhythmically brighten and dim, has opened new avenues for research. These pulsations arise from waves traveling inside the star, which are sensitive to the star's internal structure and conditions. By analyzing pulsations, astronomers perform a type of stellar ultrasound, called asteroseismology, to probe deep beneath the surface. Asteroseismology reveals core composition, density gradients, and thermal profiles. In ultramassive white dwarfs, this technique can distinguish between carbon-oxygen cores and oxygen-neon-magnesium cores, refining models of their evolution and cooling. Another captivating topic is how these stars crystallize. At the extreme densities inside ultramassive white dwarfs, the plasma of ions begins to form a crystalline lattice as the star cools. This phase change releases latent heat, slowing the cooling process and affecting the star's brightness and temperature over time. This crystallization process, confirmed by recent observations, is one of the first examples of quantum physics impacting observable stellar behavior. Understanding it better could help clarify the age and evolution of white dwarfs throughout the galaxy. Recent discoveries also suggest that some ultramassive white dwarfs may have formed through mergers of two less massive white dwarfs. When two white dwarfs orbit closely, gravitational wave emission causes them to spiral inward and merge. This merger can produce a single ultramassive white dwarf, sometimes with rapid rotation and strong magnetic fields. These merged objects differ significantly from white dwarfs that evolved from a single star. They might show unusual surface compositions, rotational speeds, or magnetic properties. Understanding these differences is important for interpreting observations and connecting them to stellar population histories. The mergers also tie into the broader story of stellar death and rebirth. Depending on the total mass and conditions, mergers can trigger supernova explosions or create stable ultramassive white dwarfs. This duality adds complexity to our models of supernova progenitors and binary star evolution. While ultramassive white dwarfs are fascinating in their own right, their existence also offers a testing ground for fundamental physics. They exist at the edge where classical physics meets quantum mechanics and relativity, forcing scientists to refine theories about how matter behaves under intense gravity and pressure. For example, the behavior of electrons in the dense cores of ultramassive white dwarfs must be described by quantum degeneracy pressure, a concept from quantum mechanics that prevents the star from collapsing. This pressure acts independently of temperature, which is why white dwarfs don't collapse further even when they cool down. But at the extreme densities of ultramassive white dwarfs, new quantum effects might come into play, including electron capture and changes in nuclear composition. These processes could influence whether a star remains stable or collapses further into a neutron star. Another area of active research is how rotation affects these stars. A rapidly spinning white dwarf generates centrifugal forces that counteract gravity, potentially allowing it to exceed the classic Chandrasekhar mass limit. Measuring rotational velocities and understanding their influence is a key challenge for astronomers. Magnetic fields add another layer of complexity. Some ultramassive white dwarfs exhibit magnetic fields billions of times stronger than Earth's, which may alter their structure and evolution. Strong magnetic pressure can provide additional support against gravitational collapse or cause anisotropies in shape. The origin of these magnetic fields is still debated. They might be inherited from the progenitor star, amplified during a merger event, or generated by dynamo mechanisms inside the star. Understanding these fields could explain many puzzles about white dwarf evolution. Moving from physics to cosmology, ultramassive white dwarfs contribute to the universe's chemical evolution. Through processes like novae and supernovae, they enrich the interstellar medium with elements heavier than helium, elements necessary for planets, biology, and life as we know it. The cycle of matter, from star formation to death and back to new stars, depends on these enrichment processes. Ultramassive white dwarfs, by influencing when and how supernovae occur, play an important role in shaping galaxies. Even more intriguing, some recent studies suggest ultramassive white dwarfs might be involved in producing certain types of high-energy cosmic phenomena. For example, they could be sources of unusual X-ray or gamma-ray bursts linked to magnetic activity or accretion events. Astronomers are still exploring these possibilities, but if confirmed, ultramassive white dwarfs would represent a new class of cosmic engines, helping explain mysterious transient events observed across the universe. The quest to understand ultramassive white dwarfs is ongoing, with each new discovery raising more questions. Future telescopes, both ground-based and space-based, will provide sharper images, more detailed spectra, and better timing measurements. Coupled with advances in computational modeling and gravitational wave astronomy, the study of ultramassive white dwarfs promises to illuminate not just the fate of stars, but the fundamental workings of matter and the evolution of the cosmos itself. These stars may be small remnants, but their impact stretches across space and time, bridging the smallest scales of quantum mechanics to the grandest scales of galaxies and the universe. Their mysteries invite us to look deeper, think harder, and marvel at the complex beauty of the cosmos. Ultramassive white dwarfs push the boundaries of what we understand about how matter behaves when squeezed to extremes. When you imagine a star about the size of Earth but packing more than 1.3 times the Sun's mass, the forces inside it are beyond everyday experience. The atoms are crushed so tightly that electrons form a dense sea, exerting a pressure called electron degeneracy pressure, which holds the star up against gravity. This pressure is a quantum effect. It's not about heat or radiation, but about the basic rules of physics that stop electrons from being in the same place at the same time. But as the mass of a white dwarf approaches the Chandrasekhar limit, roughly 1.4 times the Sun's mass, the electron degeneracy pressure starts to struggle. Gravity gets stronger, and the star gets denser and denser. Ultramassive white dwarfs sit just below this limit, balanced on a knife's edge. This balancing act makes them incredibly interesting because tiny differences in mass or internal conditions can push the star toward collapse. One key question researchers are exploring is what happens inside these ultramassive white dwarfs in their cores. Instead of the usual carbon-oxygen core found in lighter white dwarfs, ultramassive ones often have cores rich in oxygen, neon, and magnesium. This is because their massive progenitor stars went through more complex nuclear burning stages before shedding their outer layers. Oxygen-neon-magnesium cores have different physics compared to carbon-oxygen cores, particularly in how they respond to rising pressures and temperatures. The density inside these cores can trigger electron capture processes, where electrons are forced into atomic nuclei, transforming protons into neutrons. This process reduces the electron degeneracy pressure and can trigger the collapse of the star into a neutron star. In this way, ultramassive white dwarfs are like a cosmic, ticking time bomb, but one that may take billions of years to reach its final fate. Some of these stars may quietly collapse without a big explosion, while others could explode as a type of supernova. This variety challenges astronomers to understand the exact pathways leading to each outcome. Another fascinating property of ultramassive white dwarfs is their cooling behavior. White dwarfs don't have any internal energy source once nuclear fusion stops. They cool by radiating away their stored heat over billions of years. But the rate at which they cool depends on their composition and internal processes. In ultramassive white dwarfs, the process of crystallization in the core, where ions lock into a solid lattice, releases extra heat. This latent heat slows the cooling, creating a crystallization plateau. Observing this effect helps astronomers estimate the ages of these stars more accurately, and provides a direct test of solid-state physics under extreme conditions. The discovery of pulsations in some ultramassive white dwarfs adds another layer to the story. These stars vibrate with periods of minutes to hours, producing brightness variations. These pulsations are caused by gravity-driven waves inside the star, and by studying them, astronomers can infer the internal structure, including core size, composition, and layering. This astroseismology has become a powerful tool. The patterns of pulsations are like fingerprints, unique to each star's internal makeup. This technique can even detect the presence of thin surface layers of hydrogen or helium and reveal if the star is rotating rapidly. Rotation itself plays a significant role in ultramassive white dwarfs. Fast rotation can provide additional support against gravity, allowing the star to hold more mass without collapsing. Some ultramassive white dwarfs spin so quickly that their shapes become slightly flattened due to centrifugal forces. The origin of such rapid spin could be from the star's original rotation, or the result of a merger between two white dwarfs. When two white dwarfs collide and merge, they combine their mass and angular momentum, often producing a rapidly rotating ultramassive white dwarf. These mergers are exciting because they can produce unusual stars with strong magnetic fields, rapid spin, and sometimes unusual chemical signatures. Understanding these objects helps fill in the puzzle of how white dwarfs evolve in binary systems, and how they might become supernovae or neutron stars. Speaking of magnetic fields, ultramassive white dwarfs often have some of the strongest magnetic fields seen in stars. These magnetic fields can be billions of times stronger than Earth's and influence the star's cooling, rotation, and surface phenomena. The magnetic field can trap charged particles, producing intense radiation and influencing the star's brightness. In some cases, the field can channel accreting material onto magnetic poles, creating hotspots and pulsating X-ray emissions. Scientists are still working out how these magnetic fields form and evolve. Some think the fields are remnants from the star's earlier life, while others believe they arise or get amplified during white dwarf mergers. Ultramassive white dwarfs also teach us about the lives and deaths of stars in binary systems. In many cases, these white dwarfs exist in pairs or in systems where they can pull material from a companion star. When a white dwarf accretes material, it can experience surface explosions called novae, where accumulated hydrogen ignites in a runaway fusion event. Over time, this accretion can push the white dwarf's mass closer to the Chandrasekhar limit, raising the possibility of a supernova. Type I supernovae are critical to astrophysics because they serve as standard candles for measuring cosmic distances. However, the exact origins and triggering conditions for these supernovae remain an active area of research, and ultramassive white dwarfs are central to understanding this mystery. In addition to their role in supernovae, ultramassive white dwarfs may be sources of mysterious cosmic phenomena such as fast radio bursts or unusual X-ray transients. While evidence is still preliminary, the extreme conditions present in these stars make them prime candidates for driving energetic events. On a broader scale, ultramassive white dwarfs contribute to the chemical evolution of galaxies. Through their supernovae or mass loss events, they spread elements like oxygen, neon, and magnesium into the interstellar medium, enriching the raw material for future star and planet formation. These processes link the life cycles of stars to the development of planets, and ultimately the conditions necessary for life. By studying ultramassive white dwarfs, we better understand the cosmic origins of the elements essential for biology. The study of ultramassive white dwarfs is an ongoing frontier in astrophysics. With upcoming telescopes like the James Webb Space Telescope and the Vera Rubin Observatory, astronomers will be able to observe these stars with unprecedented clarity and detail. New data will help resolve current debates about their formation, composition, and final fate. Improved theoretical models, powered by supercomputers, will simulate the extreme physics inside these stars to predict their behavior more accurately. Gravitational wave astronomy, which detects ripples in spacetime caused by massive objects like merging white dwarfs, adds a new dimension to studying ultramassive white dwarfs. Future detections of white dwarf mergers will provide direct insight into how many ultramassive white dwarfs form this way. The story of ultramassive white dwarfs is one of extremes of density, magnetism, rotation, and gravity. Yet, despite their compact size, they have an outsized impact on our understanding of stellar death, cosmic chemistry, and even the expansion of the universe. They are laboratories for physics under conditions impossible to recreate on Earth, bridging quantum mechanics and astrophysics. Each discovery opens new questions and deepens our appreciation for the complexity and beauty of the cosmos. Ultramassive white dwarfs remind us that even the smallest stars can hold secrets that stretch across space and time, challenging our knowledge and inspiring curiosity about the universe we live in. These stars, for all their small size, are like frozen echoes of ancient cosmic violence, leftovers from stars that lived fast, died dramatically, and left behind something strange and extreme. And while they look quiet from far away, the truth is, they're still changing, still evolving in ways we're only starting to uncover. Some are slowly rotating, their magnetic fields bending space and affecting nearby material. Some are spinning faster than thought possible, twisting and warping under their own forces. Every ultramassive white dwarf out there might be on the verge of something: collapse, explosion, or perhaps something we haven't imagined yet. One of the biggest puzzles they raise is how they got so heavy without turning into neutron stars. Theoretically, stars heavier than about 8 to 10 times the Sun's mass end their lives in supernova explosions and leave behind neutron stars or black holes. Yet somehow, some stars, through complex, finely tuned processes, manage to avoid a supernova and leave behind ultramassive white dwarfs instead. That means their evolution must have been a balancing act, enough mass to create high pressures and heavy elements inside, but not quite enough to cross the tipping point into total collapse. In some cases, the answer might lie in how these stars lost mass at the end of their lives. A powerful stellar wind, or mass transfer in a binary system, could strip enough outer material to let the core cool and stabilize as a white dwarf before it could collapse. Other times, it might be that two average mass white dwarfs merge slowly enough to form a new ultramassive white dwarf instead of exploding in a thermonuclear blast. Mergers like that are especially interesting because they also tie into the mystery of strong magnetic fields. Some astronomers believe that when two white dwarfs merge, their swirling plasma and interacting magnetic fields can combine to form an ultramassive white dwarf with a magnetic field so strong, it reshapes how energy moves through the star's outer layers. And once these fields are in place, they don't fade easily. They can stay locked in for billions of years, silently sculpting the star's behavior. There's also the question of what happens if something goes wrong, if the star tips over the line into instability. If a white dwarf exceeds the Chandrasekhar limit, even by a tiny bit, gravity wins. The electrons can no longer hold off collapse, and the star might implode into a neutron star. But what's fascinating is that this might happen quietly. Some researchers think ultramassive white dwarfs could collapse directly into neutron stars without a supernova, just vanishing from view in a single, sudden transition. No bright explosion. No warning. Just silence and gravitational collapse. Or, in other cases, the collapse might trigger a peculiar kind of supernova, one that doesn't quite match the standard models. These electron capture supernovae are a subject of active research. They could explain some rare cosmic explosions that look different from normal supernovae, dimmer, slower, with unusual chemical signatures. If ultramassive white dwarfs are behind these, they might be key to solving long-standing supernova mysteries. But collapse isn't the only possible fate. Some ultramassive white dwarfs might instead cool for billions of years until they become black dwarfs, theoretical remnants that have radiated away all their heat and no longer emit light. These objects don't exist yet, because the universe isn't old enough for any white dwarf to have cooled that much. But in the far future, after trillions of years, black dwarfs might become the last structures left, cold, dark relics of stars that once burned brightly. Studying ultramassive white dwarfs also helps test some of the most extreme physics we know, particularly the limits of quantum mechanics and general relativity. The incredibly dense matter inside these stars behaves according to the rules of quantum degeneracy. But when you pack enough mass into a small space, gravity also starts to bend spacetime significantly. This combination of quantum physics and gravity makes ultramassive white dwarfs one of the closest natural laboratories we have to studying the edge between known and unknown physics. Even tiny details matter. The rate at which electrons are captured, the type of ions that form in the star's interior, how those ions interact with the dense electron sea, all of these influence whether a white dwarf stays stable or tips into collapse. One recent theory even suggests that dark matter might accumulate in the cores of white dwarfs over time, subtly affecting their evolution. If that's true, ultramassive white dwarfs might act as indirect detectors for one of the most mysterious substances in the universe. Another area of active research is related to the exact threshold at which a white dwarf becomes too massive. The Chandrasekhar limit is a critical number, but it's not one size fits all. It depends on the star's composition. Carbon-oxygen cores reach instability at a slightly lower mass than oxygen-neon-magnesium cores, which are more resistant to compression. This means that two ultramassive white dwarfs of similar mass could have completely different fates, simply because of what they're made of. And this difference becomes even more important when you factor in rotation. A fast-spinning ultramassive white dwarf might resist collapse longer than a slowly spinning one. In fact, some researchers believe rotation can push the mass limit above the normal Chandrasekhar threshold, creating so-called super Chandrasekhar white dwarfs that defy standard models. These stars might look stable for a time, until they lose angular momentum, slow down, and suddenly become unstable. Imagine that, a star sitting calmly for 1 billion years, only to collapse instantly because it's slowly spun down over time. This kind of delayed collapse could explain some supernovae that seem to appear out of nowhere in old stellar populations. It could also hint at an invisible countdown happening inside ultramassive white dwarfs all over the universe. There's something strangely poetic about that, a quiet, dense star, holding itself together with quantum pressure and spin, fighting gravity for as long as possible. And eventually, that battle ends not with a bang, but with a collapse into a new state of matter. This constant tension, between gravity and pressure, heat and cold, stability and collapse, is what makes ultramassive white dwarfs so compelling. They're cosmic cliffhangers, frozen in time between different possible futures. And because their fate is so finely balanced, even small changes in their environment could trigger something big. A close stellar flyby, a small amount of new material from a nearby star, a shift in internal structure. Any of these might be enough to push the star toward a supernova or a silent collapse. And we might never know until after it happens. That makes every ultramassive white dwarf we discover a kind of ticking clock, waiting to see which path it takes. As we keep studying these stars with better instruments and better models, we'll get closer to answering the deeper questions. How often do white dwarfs merge? How do magnetic fields evolve in extreme conditions? What's the true mass limit before collapse? And are there even heavier white dwarfs out there that we haven't found yet, stars teetering right on the edge of physics itself? The journey of understanding ultramassive white dwarfs is still just beginning. Every new discovery opens more doors, more questions, and more strange possibilities that stretch our imagination about how the universe works. Some of the strangest ideas emerging from research on ultramassive white dwarfs go beyond what we used to think was even possible. There's a growing theory that some of these stars might actually be masquerading as something else entirely. Because their surface temperatures, spectra, and sizes can overlap with other objects, they might not even appear white in the way we imagine. They could be misclassified, overlooked, or misunderstood in data that astronomers have already collected. This opens the door to a wild possibility. What if we've already seen hundreds of these stars, but just didn't realize what we were looking at? Their small size also adds to the difficulty of detection. Even though they pack more mass than the Sun, many ultramassive white dwarfs are no bigger than Earth. That's like stuffing an entire mountain into a marble. From light years away, they're incredibly faint and hard to distinguish. It takes precision instruments and clever indirect methods to even spot them. And still, they continue to surprise us. One of the most fascinating things we've seen is how these stars affect their environments. For example, if an ultramassive white dwarf is part of a binary system, the gravitational tug it exerts on its companion can create tidal effects strong enough to distort the shape of the other star. It can strip matter from it, twist its orbit, or cause it to spiral in slowly. These changes don't just affect the stars involved, they also release gravitational waves, the ripples in spacetime that were predicted by Einstein and only recently detected directly by instruments like LIGO and Virgo. These gravitational waves give us a new way to study white dwarfs without even seeing them directly. By analyzing the patterns of these ripples, astronomers can estimate the masses, distances, and behaviors of ultramassive white dwarfs all across the galaxy. And this is just the start. In the future, with better gravitational wave detectors, we might be able to map out entire populations of invisible white dwarf binaries, hiding in the background of the cosmos. Another weird idea: some ultramassive white dwarfs might be the remnants of stars that never went supernova because of exotic conditions early in the universe. In the young universe, stars had different compositions. They were made almost entirely of hydrogen and helium, with few heavy elements. These stars, called population 3 stars, might have evolved differently, losing mass in strange ways, or burning unusually hot and fast. If some of them ended as ultramassive white dwarfs, they could be among the oldest surviving stellar remnants, ancient fossils of the universe's youth. If true, studying them could give us a direct glimpse into the physics of the early cosmos. It's like having a time machine. Their cores would preserve the nuclear products of a very different era, untouched by billions of years of evolution elsewhere in the galaxy. By decoding their light, we could reverse engineer the history of how stars formed when the universe was still a baby. And it's not just their past that matters. The futures of these stars are just as strange. One possibility is that some ultramassive white dwarfs could form crystal cores. As they cool, their densely packed atoms begin to lock into a crystalline structure, something like a giant diamond floating in space. In fact, one white dwarf called BPM 37093 is suspected of being partially crystallized, a star-sized diamond weighing more than 10 billion trillion carats. But in ultramassive white dwarfs, this process would be even more intense. Their higher pressures could make them crystallize faster, locking up energy and slowing down the cooling process. This crystallization also affects how the star vibrates. White dwarfs naturally ring with tiny pulsations, like celestial bells. These vibrations carry information about the star's interior, and by studying them, scientists can essentially do an ultrasound of the star, probing its structure layer by layer. This field, called astroseismology, is giving us direct insight into what these ultra-dense remnants look like on the inside, something that was once thought impossible. But here's where it gets even stranger. Some of these stars don't just crystallize quietly. There's evidence that in the deep interiors of ultramassive white dwarfs, the atoms might form something even more exotic, a quantum fluid where particles behave like waves, and normal physics starts to break down. This is no ordinary matter. It's something more like a mix between solid, liquid, and plasma, governed by the strangest rules in quantum mechanics. Understanding this would not just improve our models of stars, it could have ripple effects in fields like materials science, nuclear physics, and even quantum computing. Because if we can model matter under extreme pressures and densities, we can start designing materials here on Earth that take advantage of those same principles. One huge mystery still lingers: why don't we see more ultramassive white dwarfs? If they're a natural part of stellar evolution, we should expect to find many of them. But so far they're rare. That raises the possibility that most of them don't stay white dwarfs for long, that maybe they really are ticking time bombs, destined to collapse into neutron stars or ignite into supernovae. It might also mean that we're just bad at finding them. There's also the possibility that we're biased in our observations. Most of our surveys are looking for normal, white dwarfs, average sizes, average masses, average temperatures. Ultramassive white dwarfs might fall outside the typical filters. They could be hidden among misclassified objects, their true nature disguised by strange spectra or unusual motion. This gets into the philosophy of science. Are we missing things because we're not asking the right questions? Because we've trained our machines to look for what we already expect? Ultramassive white dwarfs challenge our assumptions, not just about stars, but about how we do science. And this is why they matter so much. Every time we find one, it's like discovering a crack in our current models. A place where nature says, "You thought you understood, but there's more going on." These cracks are where science grows, where the weird stuff lives, where the biggest leaps in knowledge can happen. These stars might even change how we think about death, not just stellar death, but cosmic death. Because they show that the end isn't always final. That remnants can hang on, evolve, and become something strange and powerful in their own right. The universe doesn't throw things away. It recycles them in weird and wonderful ways. Ultramassive white dwarfs are reminders of that. They are leftovers from colossal energy, compressed into something smaller than a planet but heavier than the sun. They hold the ashes of nuclear fire, the echoes of collapse, and the seeds of future explosions. They are the ghosts of stars, and maybe, one day, they'll come back to life, in bursts of light, or collapse, or as something we can't even name yet. And as long as they're out there, we'll keep looking up, trying to understand. What's really wild is how ultramassive white dwarfs could end up being the key to understanding something much, much bigger, not just the life and death of stars, but the fate of the universe itself. You see, every white dwarf is slowly cooling down. Over billions and trillions of years, they'll radiate away their heat until they become black dwarfs, cold, dark, and almost invisible. But the universe isn't old enough for a single black dwarf to exist yet. So when we look at ultramassive white dwarfs, we're essentially seeing a preview of the far future, a future that hasn't even happened yet anywhere in the cosmos. That makes these stars like time capsules. By studying how they cool, how they evolve, how they emit light, and how their internal structures shift over time, we're building models of what matter will look like in the distant universe, when galaxies fade and the last light slowly dies. It's haunting, honestly, imagining a universe that's just cold corpses of stars, no fusion, no light, no life. And at the center of that slow death, ultramassive white dwarfs would be among the last objects still radiating any warmth. And it makes you wonder, if the universe lasts long enough, will these ultramassive white dwarfs become the last sources of energy? Could future civilizations, if they exist trillions of years from now, huddle near these fading stars for warmth? Could they somehow draw power from their gravity, their magnetic fields, or the tiny amounts of heat they still release? It sounds like science fiction, but it's actually just basic physics extended forward in time. These stars may outlive everything else. There's another angle that's been getting attention lately: magnetic fields. Some ultramassive white dwarfs have magnetic fields that are thousands, or even millions of times stronger than Earth's. These aren't just side effects, they may be crucial to how these stars form, evolve, and even resist collapse. In fact, there are models suggesting that strong magnetic fields might be the only reason some ultramassive white dwarfs can exist without collapsing into neutron stars. The magnetic pressure could help balance the gravitational pressure, like invisible scaffolding holding up the star. This opens up a whole new branch of astrophysics, exploring how magnetism affects the structure of matter under extreme pressure. Think about this: on Earth, strong magnets can do incredible things. Levitate objects, disrupt electronics, even affect the properties of atoms. Now imagine that scaled up to something with the mass of the Sun. The internal physics would be completely different from anything we've ever seen. It could mean that these stars are hosting types of matter we haven't even discovered yet, not because they're far away, but because we've never built labs powerful enough to replicate those conditions. The cores of ultramassive white dwarfs might be filled with superfluid neutrons, strange forms of crystallized carbon, or even exotic states of plasma that break the rules we're used to. Every time we push deeper into these stars with our models, the rules seem to bend a little more. And these magnetic fields don't just stay inside the star. They extend out into space, forming massive magnetospheres that can trap charged particles, redirect radiation, and maybe even influence the star's cooling process. It's like each ultramassive white dwarf has its own magnetic weather system, a slow, powerful, swirling storm of particles and fields. This can also lead to strange surface features, like star spots, but far more extreme. Some white dwarfs show uneven cooling, with regions on their surface that are thousands of degrees hotter or colder than others. These temperature differences can produce bizarre light curves when the star rotates, causing it to pulse or flicker in ways that look almost artificial. For years, some of these flickering stars were thought to be alien signals, just because they were so regular and weird. Now we know they're natural, but still completely wild. And here's another thing: sometimes, ultramassive white dwarfs don't go quietly. Under certain conditions, they might ignite runaway nuclear reactions in their outer layers. Not enough to destroy the star, but enough to create flashes of light, blasts of particles, or shifts in their structure. These mini-explosions could happen randomly, triggered by changes in temperature or pressure deep inside the star. Some researchers think this might explain certain types of fast, unexplained flashes seen in deep sky surveys, bursts of light that appear for a moment, then vanish. They might not be black holes, or neutron stars, or anything exotic, just ultramassive white dwarfs having sudden outbursts. If true, it means these stars are far more dynamic than we thought. And the more we look, the more we realize how many mysteries still surround them. Like, what happens if two ultramassive white dwarfs collide? We know white dwarf mergers can produce type I supernovae, but if both stars are already near the Chandrasekhar limit, the outcome might be even more extreme. Maybe they collapse instantly into a neutron star, maybe they form a new kind of object, or maybe, just maybe, they unleash a kind of explosion we haven't classified yet. Some scientists have speculated that ultra-powerful gamma-ray bursts, which are usually linked to black holes or neutron star mergers, might sometimes be caused by these ultra-dense white dwarf collisions. It's not confirmed yet, but it would fit some of the weirder burst profiles we've seen: short, intense, with strange afterglows. This brings us to another mind-blowing idea. What if ultramassive white dwarfs aren't just the end of something, but the beginning of something else? Think about this. We usually see white dwarfs as the last stage of stellar evolution, a kind of permanent retirement for a star. But if these ultramassive white dwarfs can ignite under pressure, if they can collapse into new forms, if they can merge and produce bursts of energy, then maybe they're not just stellar corpses. Maybe they're seeds. Seeds of neutron stars, seeds of supernovae, maybe even seeds of something stranger, like quark stars, or primordial black holes. In this way, ultramassive white dwarfs become the cosmic equivalent of phoenixes, born from fire, dying in silence, then reigniting into something new. They aren't just leftovers. They're the hidden gears in the machinery of the universe, quietly driving change, shaping the structure of galaxies, and maybe rewriting the story of how stars live and die. It's humbling, really. We used to think of stars as bright points of light in the sky. But the more we learn, the more complex they become, and ultramassive white dwarfs are some of the most complex of all. They defy the rules, blur the lines between different classes of objects, and force us to rethink what we thought we knew. They're quiet, but powerful. Old, but not dead. Small, but massive. And hidden in their dense cores, behind layers of extreme physics and unimaginable pressure, lies some of the most important information in the entire universe, waiting for us to unlock it. Their presence also shakes up how we think about the population of stars in our galaxy. If ultramassive white dwarfs are more common than we originally thought, then maybe we've underestimated how many stars reach the upper limit of stellar mass before quietly ending their lives. This matters because it changes the way we estimate things like supernova rates, the chemical evolution of galaxies, and even the timing of when heavier elements like iron and nickel were seeded into the cosmos. It's a ripple effect. One small correction in white dwarf populations could echo through the entire timeline of galactic development. Another key point that's starting to get attention is the role of binary systems. A surprising number of ultramassive white dwarfs are found in binary pairs, either with other white dwarfs, or with main sequence stars, red dwarfs, or even neutron stars. This changes the game, because when two stars are orbiting each other closely enough, they can exchange mass over time. One star can pull matter from the other in a slow, steady flow, or in violent bursts. That process can crank up the mass of a white dwarf way beyond what it started with, eventually pushing it into the ultramassive category. These binary interactions are also responsible for some of the most dramatic events in astrophysics. In some cases, if a white dwarf accretes too much mass too quickly, it can ignite a thermonuclear runaway, resulting in a massive explosion known as a Type I supernova. But in the case of ultramassive white dwarfs, where mass and pressure are already teetering on the edge, this process becomes even more unstable. The thresholds for collapse, ignition, or transformation into another type of stellar object become razor-thin. A tiny change in temperature, or the rate of accretion, could be the tipping point that triggers a complete transformation. What's fascinating is that these transformations might be happening all around us, we just don't recognize them yet. Some of the sudden, unexplained high-energy events picked up by telescopes like Swift and Chandra may be linked to ultramassive white dwarfs reaching critical mass or undergoing sudden shifts in structure. These stars don't announce themselves like supernovae do. They don't always explode in a bright, obvious flash. Sometimes they collapse inward, almost silently, forming neutron stars or even black holes without the kind of fireworks we're used to seeing. And because ultramassive white dwarfs are so faint compared to active stars, we may have missed thousands, maybe millions, of them. They don't give off much light, and they don't move quickly. Unless we're specifically looking for their gravitational pull, or the faint blue-white signature of their cooling heat, they can slip right past our surveys. It's only with modern infrared and ultraviolet telescopes, along with precise parallax measurements from missions like Gaia, that we're finally starting to spot them. Even then, identifying one isn't easy. You have to measure its temperature, luminosity, mass, and radius with extreme accuracy, and then feed that data into complex models of stellar structure. A tiny error can throw the whole estimate off. That's why most of the ultramassive white dwarfs we've confirmed have come from painstaking observational work, hundreds of hours of data, processed with cutting-edge algorithms, double-checked with multiple instruments. It's not glamorous work, but it's the only way we're starting to map out this hidden population of stellar giants. Some of the most exciting finds have come from citizen science projects, where amateur astronomers help process telescope data or flag unusual light curves. A few ultramassive white dwarfs have been spotted this way, hiding in plain sight, but overlooked until someone noticed something weird in their brightness or movement. It's a reminder that space exploration isn't just done by billion-dollar observatories. Sometimes it's someone in their backyard, staring at a blinking dot on a screen. The more we dig, the more unusual traits we uncover. For example, some ultramassive white dwarfs rotate incredibly slowly, taking days, or even weeks, to complete one spin. Others rotate so quickly that they're almost at the breaking point. This spin rate affects their structure, their cooling, and their magnetic fields. A fast-spinning white dwarf might be slightly flattened at the poles, or have hot spots at its equator, caused by centrifugal force pulling the surface outward. Some even show signs of precession, a slow wobble in their rotational axis, like a spinning top just before it falls over. This kind of movement can cause the light they emit to shift or flicker, making them even harder to study. But it also provides valuable clues about their internal makeup, and whether their mass is distributed evenly, or if there are denser pockets lurking inside. One mystery that hasn't been solved yet is how ultramassive white dwarfs manage to stay intact at such high densities. We know about electron degeneracy pressure, which keeps white dwarfs from collapsing, but at these extreme masses, that pressure should start to fail. That's why the Chandrasekhar limit exists. It's the point where gravity becomes stronger than the forces holding the atoms apart. So how do ultramassive white dwarfs defy that limit? There are a few theories. One is that they contain exotic forms of matter, maybe even a phase of carbon or oxygen that only exists under extreme pressure, more resistant to collapse than normal matter. Another idea is that strong magnetic fields add extra support, boosting the internal pressure without needing more mass. And there's even the possibility that some of these stars are only temporarily stable, slowly shifting toward collapse over millions of years, but just stable enough for us to observe them in their in-between state. This delayed collapse theory is fascinating because it suggests that some ultramassive white dwarfs are like ticking time bombs. They're not exploding right now, but they could, someday, with little warning. Maybe in 10,000 years. Maybe in 10 million. But when they do, the event would be dramatic, a sudden, high-energy shift that sends ripples through the galaxy. That brings up another weird possibility: gravitational waves. We usually associate these waves with black holes or neutron star mergers, but it's possible that ultramassive white dwarfs, especially in tight binaries, could produce their own gravitational wave signatures. If two of them orbit each other closely, they'll spiral inwards over time, losing energy to space itself. Eventually they'll merge, and the moment of that merger would send a ripple through the fabric of space-time. Detecting those ripples would require instruments far more sensitive than what we currently have. But future missions, like LISA, the Laser Interferometer Space Antenna, could pick them up. And if we can detect gravitational waves from white dwarf mergers, we'll be able to map an entirely new kind of cosmic interaction, one that's silent, invisible, and utterly profound. It would also help us detect white dwarfs in galaxies beyond our own, maybe even in the early universe. If ultramassive white dwarfs formed more often in the past, when massive stars were more common, then we should see their remnants scattered across ancient galaxies. They might be hiding in elliptical galaxies, or at the centers of globular clusters, slowly cooling over billions of years. Their gravitational effects might be the only trace they leave behind. And even then, their influence lingers. They help seed the galaxy with heavy elements. They shift the dynamics of binary systems. They help regulate the pace of star formation by injecting energy into their surroundings when they form. They might even help explain certain dark matter anomalies by mimicking its gravitational pull in some regions of space. They even affect how we think about time itself. Because white dwarfs are so predictable in their cooling patterns, astronomers use them as cosmic clocks. The temperature of a white dwarf tells you how long ago the star died. But if ultramassive white dwarfs cool at a different rate than normal ones, either faster because of their compactness, or slower because of internal energy from exotic matter, that throws off those timelines. It means that some star clusters we thought were 9 billion years old might be 1 billion years older, or younger. And that's not a small thing when you're trying to measure the age of the universe. And that brings up the wild idea: what if some of the most ancient objects we've ever found aren't black holes, but ultramassive white dwarfs? We assume black holes are the final endpoint for the most massive stars. But what if some of those stars instead formed ultramassive white dwarfs and just never collapsed? It's a fringe idea, but there's growing speculation that some objects we've labeled as black holes, especially the smaller ones, might actually be incredibly dense white dwarfs that still haven't crossed the critical threshold. Think about what that would mean. All this time, we've believed black holes are dominant in certain areas of the galaxy. But maybe, just maybe, some of those black holes are just stars frozen in place, holding on to their identity, defying the fate we thought was unavoidable. It wouldn't just change how we look at stellar evolution, it would change how we define death in space. And as strange as it sounds, some researchers even wonder whether ultramassive white dwarfs could be homes for planets. Yes, that's right, planets. Normally, white dwarfs are thought to destroy their planetary systems when they form. Their intense heat, radiation, and gravity blow apart nearby objects. But there are exceptions. We've already found planets orbiting white dwarfs, scarred and scorched, yes, but still there. If that can happen around normal white dwarfs, could it also happen around ultramassive ones? Imagine a planet orbiting an object the size of Earth, but with the mass of 1.3 suns. Imagine the gravity it feels. The way time moves more slowly on that world. The radiation environment would be extreme. But if a planet were far enough away, it might survive. Maybe even evolve. That opens the door to some of the strangest possibilities in astrophysics. Could life exist around a white dwarf? Could it adapt to the remnants of a dead star? No one knows. But there are teams out there, using telescopes like TESS and JWST, scanning white dwarfs for signs of orbiting planets. And a few candidates have already popped up. Some show dips in brightness that could mean a planet is passing in front of the star. Others show weird chemical signatures in their light, suggesting that rocky debris or planetary fragments are still nearby. One star, GD356, even shows signs of magnetic activity that something could be caused by a Jupiter-sized planet orbiting within its magnetic field, generating electric currents like a giant dynamo. If true, that's a massive discovery. It would mean that not only can planets survive the death of a star, they can interact with the corpse in strange and powerful ways. It would mean that white dwarfs don't just mark the end of a solar system. In some cases, they might mark the beginning of a completely new kind of stellar system. One shaped by exotic physics, extreme gravity, and maybe, just maybe, something entirely unknown. And this is where the mystery of ultramassive white dwarfs gets really deep. Because we're not just talking about odd stars anymore. We're talking about relics. Fossils of the early universe. Traces of stellar generations that lived and died before our solar system even existed. And the strangest part is, they're still here. Cooling, glowing, drifting silently in the dark. These are stars that challenge the boundary between life and death. Between stability and collapse. Between light and silence. And they sit right on that edge, sometimes for billions of years, frozen in time. The fact that we can study them at all is amazing. The fact that we're just starting to realize how weird they are, that's the real thrill. Some astronomers now believe ultramassive white dwarfs might be more than just an odd category of star. They might be a key to unlocking something deeper about the universe itself. Maybe they formed in a different way than normal stars. Maybe they came from the early universe, before galaxies had finished forming. Maybe they carry information, deep inside their cores, that no other object does. Maybe, like cosmic hard drives, they've stored the fingerprint of a universe we never got to see. This idea gets a little speculative, but it's not science fiction. Some theoretical physicists believe that conditions inside the most massive white dwarfs might allow for quantum gravitational effects to be detectable in the future. These are places where general relativity and quantum mechanics collide. Places where the known laws of physics start to warp. If we could probe deep enough into one of these stars, if we could somehow study their cores directly, we might uncover the conditions that existed moments after the Big Bang. That's why ultramassive white dwarfs are suddenly so important. They're not just cosmic leftovers. They're laboratories. Natural test beds for extreme physics. And maybe, just maybe, they're keys to questions we've been asking for a long, long time. Why does the universe have the structure it does? Why do certain elements appear in the proportions they do? Why do some stars explode, and others fade away? What happens at the edge of stability? Where does gravity end and something else begin? These stars don't give up their secrets easily. They don't shout. They don't burst into brilliance like supernovae. They whisper. They sit there in silence, challenging us to listen more closely. To invent better tools. To ask better questions. And slowly we are. And that slow unraveling of their secrets is one of the most fascinating parts. Because unlike things like black holes that dominate headlines with their drama and their extremes, ultramassive white dwarfs are quieter. They don't rip stars apart or bend space so hard that light can't escape. Instead, they just sit there, impossibly dense, impossibly small, and yet still burning with the last whispers of heat from a life long gone. That quietness makes them easy to overlook, but the more you study them, the more you realize they could be hiding some of the deepest truths in the universe. These stars are unique in the way they warp our understanding of matter itself. In everyday life, we never deal with electron-degenerate matter, the stuff that makes up white dwarfs. It's not like any solid, liquid, or gas we know. It's a form of matter where the usual rules of atoms and molecules collapse under the pressure of gravity. Electrons aren't orbiting nuclei anymore. They're crushed into a quantum sea, resisting further collapse not with mass, but with a kind of statistical pressure that only exists because of quantum rules. That's what holds a white dwarf up. That's what keeps it from turning into a black hole. But in ultramassive white dwarfs, the limits of that degeneracy pressure are tested in ways we've never seen before. These stars are sitting right at the edge of what's physically possible before the laws break down. That makes them a perfect test for understanding where quantum mechanics and gravity collide. Because normally, these two pillars of modern physics don't get along. Quantum mechanics works on tiny scales. Gravity works on huge ones. White dwarfs, especially ultramassive ones, exist in the tight space in between, where both forces are so strong that neither can be ignored. And it's here, in this razor-thin zone of stability, that some physicists believe we might find the key to unifying our understanding of the universe. That's not just a theory thrown around in textbooks, it's a goal researchers are actively pursuing. If we can understand how matter holds itself together in ultramassive white dwarfs, we might finally understand how to unify quantum theory with general relativity, the holy grail of physics. That would change everything. It could answer questions about the beginning of time, the fate of the universe, and the hidden dimensions some theories predict. Now here's another strange idea that's gaining attention. Some scientists think ultramassive white dwarfs might actually be imposters. That is, maybe they're not white dwarfs at all. Maybe there's something even stranger that just happens to look like a white dwarf from the outside. There's a theory out there that in some conditions, collapsing stars don't stop as white dwarfs or go all the way to black holes, but instead, become something in between, something exotic. These hypothetical objects go by names like quark stars, or preon stars. They'd be made not of atoms, or even neutrons, but of even smaller building blocks. If that's the case, then maybe some of the ultramassive white dwarfs we see are actually these bizarre, ultra-dense forms of matter masquerading as white dwarfs. Think about how wild that is. We look at these stars through telescopes and say, "Yep, that's a white dwarf." But maybe it's not. Maybe it's a new class of object we've never confirmed before. That's the thing about astronomy. We only ever see the light. Everything else is guesswork, built on models and theory. So if our assumptions are even a little off, we might be misidentifying entire categories of cosmic objects. And then there's the rotation. Some white dwarfs spin at incredible speeds. One was found spinning once every 13 seconds. That might not sound fast, but for a star the size of Earth, that's dizzying. If you could stand on the surface, you'd be flung off instantly. Now imagine what happens if an ultramassive white dwarf spins that fast. The centrifugal force could almost rival its own gravity. That starts to destabilize the whole structure. It starts pushing the limits of what's physically possible for a white dwarf to survive. And yet, some seem to do it. Why? How? No one really knows. Maybe magnetic fields are involved. Some ultramassive white dwarfs have magnetic fields millions of times stronger than anything we can create on Earth. These fields twist and bend light, particles, even space itself. They might help hold the star together. Or they might hide what's really going on inside, masking the processes that would normally cause collapse. Either way, it's a mystery. One thing we do know: time doesn't pass the same way near an ultramassive white dwarf. This isn't just a theoretical concept, it's a measurable effect. According to Einstein's theory of general relativity, gravity bends time. The stronger the gravity, the slower time moves. Near the surface of an ultramassive white dwarf, gravity is so strong that time slows noticeably compared to Earth. If you lived near one of these stars, you'd age more slowly than someone far away. Not by much, but enough to matter in precise measurements. We've seen this effect on GPS satellites, which have to account for the time shift due to Earth's gravity. On an ultramassive white dwarf, that effect is multiplied many times over. So when we look at these stars, we're not just looking at the past. We're looking at time itself behaving differently. At gravity stretching not just space, but history. That alone is enough to make your head spin. But there's more. Because white dwarfs, including the ultramassive kind, don't stay the same forever. Over billions of years they cool. They lose heat. They fade. Eventually, they become black dwarfs, cold, dark cinders drifting in the void. That's the end point of a white dwarf's life. But here's the twist. The universe isn't old enough for any black dwarfs to exist yet. It hasn't been long enough since white dwarfs first formed for them to have cooled all the way down. So every white dwarf we see, even the oldest ones, are still glowing faintly. We've never seen what happens at the very end. That means ultramassive white dwarfs are part of an unfinished story. They're waiting for a finale we haven't reached yet. A transformation that will only happen trillions of years from now. That alone is poetic. Stars that died long ago are still in the middle of their slow death. Still glowing. Still cooling. Still telling us secrets. And here's something else. In some rare situations, a white dwarf can actually reignite. If it pulls in enough matter from a companion star, it can reach the Chandrasekhar limit and explode as a supernova. That's called a Type I supernova, and it's one of the most important tools in modern astronomy. It's how we discovered that the universe's expansion is accelerating. But for ultramassive white dwarfs, the story is different. They're already so close to the mass limit that just a little extra matter might push them over the edge. If that happens, they don't just explode, they collapse. And when they collapse, they might not become black holes right away. Some simulations suggest they could go through strange intermediate phases. Hypernovae, magnetar formation, or even total obliteration, producing bursts of gamma rays or gravitational waves detectable across the cosmos. These events would be rare, but they'd be loud. And if we catch one in the act, it would be like watching a cosmic accident in slow motion. The final heartbeat of a star that tried to resist gravity to the very end. It's dramatic. It's tragic. And it's deeply, deeply fascinating. But perhaps the most haunting aspect of ultramassive white dwarfs is the idea that they might represent the ultimate fate of matter itself. These stars don't shine with fusion. They don't build heavier elements. They are remnants, leftovers of once glorious stars, stripped of all their fire and left to exist in silence. In them, we see what happens when nuclear power runs out. When the core collapses, when the light dies, and when all that's left is the pressure of quantum laws resisting gravity's final call. It's a reminder that everything ends, not with a bang, but with a quiet stillness. The atoms that make us, the carbon, oxygen, iron, were forged in the hearts of stars and in the explosions that followed. But those atoms only exist because stars like the ones that became ultramassive white dwarfs lived and died. And so when we look at these dead stars, we're not just seeing astronomical objects. We're seeing the fossil record of cosmic creation. We're seeing the birth certificate of the elements in our bodies. In a way, ultramassive white dwarfs are ancestral stars. They're part of our story. And their story is still unfolding. New ultramassive white dwarfs are still being found. Some are discovered by their mass, others by their heat, and some by their strange spectral signatures. They defy categorization. Some are magnetic, others are spinning. Some are cooling fast, others slowly. And then there are the ones with unusual compositions, ones that seem to have oxygen neon cores instead of the more typical carbon-oxygen ones. That points to a whole new branch of stellar evolution. One that bypasses normal white dwarf formation entirely. One that might involve exotic forms of stellar collapse that we don't yet understand. In rare cases, ultramassive white dwarfs could be remnants of binary mergers, two smaller white dwarfs that spiraled into each other and fused. That kind of event creates gravitational waves, ripples in spacetime that race across the cosmos. We've detected such waves from neutron-star mergers and black hole collisions. But if we ever caught one from white dwarf mergers, especially ultramassive ones, it would unlock a whole new type of astrophysics. Because it would allow us to map the interiors of stars not through light, but through the shape of spacetime itself. Gravitational waves are like a stethoscope to the universe's heartbeat. And ultramassive white dwarfs might be thumping along, silently, just waiting for us to listen in. Another fascinating idea is that some ultramassive white dwarfs might not cool evenly. Their magnetic fields and rotation could cause asymmetric heat loss, meaning one hemisphere could cool faster than the other. That's not just speculation. Some stars show brightness variations consistent with this. If true, it could lead to lopsided cooling, star quakes, or even crust cracking. Yes, these stars might develop a crust, like a frozen ocean of carbon, slowly hardening over billions of years. And as the crust grows, it could fracture under the immense stress, sending seismic waves across the entire star. These events, though invisible to us now, could be detectable with future telescopes. Or if they produce gravitational ripples, with future detectors more sensitive than anything we've yet built. The idea that a dead star could still tremble, still quake, still crack from its own ancient scars is stunning. It turns a static object into a dynamic, living system, just one that's living at a pace we can barely comprehend. And all this leads us to a final, profound question: what happens if you push a white dwarf too far? We know the Chandrasekhar limit defines the point at which a white dwarf can no longer support itself against gravity. It's about 1.4 times the mass of the Sun. Go past that, and collapse becomes inevitable. But what if a star comes very close to the limit, say, 1.38 or 1.39 solar masses, and just hangs there, balanced precariously between existence and destruction? These ultramassive stars might teeter at the edge for millions of years, accumulating matter slowly, spinning just fast enough, cooled just right. And then, something small tips the balance. A nearby star sheds matter. A collision jostles the system. Or a magnetic shift causes internal instability. That tiny change could be all it takes to trigger collapse. And when that happens, it might not be a slow process. It could be instantaneous. The entire star could implode in a matter of seconds, forming a black hole or exploding outward with unimaginable force. And we might never see it coming. It could happen to a white dwarf we've already catalogued. A quiet star, glowing faintly in a distant sky, suddenly disappearing or going nova, rewriting everything we thought we knew about stellar stability. In fact, this possibility has inspired some to suggest we watch known ultramassive white dwarfs more carefully. Because they could be ticking time bombs. Not in a dangerous way, none are close enough to hurt us, but in a scientific way. If one exploded or collapsed in our lifetime, it would be a once-in-history opportunity. A front-row seat to a cosmic transformation few have ever seen. That's the true power of these stars. They don't just sit there. They whisper. They threaten. They promise. They warn. They reveal. And even though they're technically dead, they might still be the most alive part of the sky. They hold within them the quantum rules of matter, the gravitational grip of collapse, and the frozen fire of stellar legacy. They are paradoxes. They are relics. They are messengers from the edge of physics. And the more we listen, the more we learn. But maybe the most mind-bending thing about ultramassive white dwarfs is what they teach us about the limits of our universe. When we see a star that's pushing up against the Chandrasekhar limit, when it's sitting right on that edge between stability and collapse, we're watching a kind of cosmic dare. Nature is saying, let's see how far we can stretch the laws of physics before they break. And ultramassive white dwarfs are the result of that dare. They sit at the intersection of gravity, quantum mechanics, and stellar evolution, and they stretch all three almost to their breaking point. This tension, between gravity pulling in and electron degeneracy pressure pushing out, isn't just some mathematical tug-of-war. It's real. It shapes the core. It compresses atoms into near incomprehensible densities. If you could take just a teaspoon of matter from one of these stars, it would weigh several tons. Not pounds, tons. That's how tightly packed the matter is. Electrons are forced into their lowest possible energy states, crushed together in a way that would destroy normal atoms. These stars are almost pure nuclei, suspended in a soup of quantum rules that we still don't fully understand. And what happens if those rules change? What if the laws of physics behave differently at those densities? That's not just a sci-fi question. Some physicists genuinely think that ultramassive white dwarfs could contain exotic forms of matter, things we've never seen in a lab. Maybe quark matter. Maybe something even stranger. The conditions at the cores of these stars are so extreme that they might open a window into physics beyond the standard model. This is why some astronomers and physicists are obsessed with these objects. Because they're more than dead stars. They're testbeds for the laws of nature. They're like giant cosmic laboratories, billions of years old, just floating out there, waiting to be studied. And as our instruments improve, our telescopes, our space observatories, our gravitational wave detectors, we're getting closer and closer to truly understanding what's going on inside them. There's also a strange quietness to them that's hard to describe. A massive star in its prime is noisy in a way. We can see its brightness, its outbursts, its fusion reactions. But ultramassive white dwarfs don't do much. They don't pulse. They don't explode, at least not yet. They just exist. Silent. Heavy. Cold. Dense. But that silence isn't boring. It's eerie. It makes you lean in. It's like walking into a room and seeing a massive safe in the middle of the floor. You don't know what's inside, but you can feel the weight of it. You can sense the danger, the mystery, the potential. That's what it feels like looking at an ultramassive white dwarf. And yet, not all ultramassive white dwarfs are totally still. Some spin. Some spin incredibly fast, faster than expected, even dangerously fast. When a white dwarf spins, centrifugal force pushes outward. If it spins too fast, it can overcome gravity and actually start shedding mass or deforming. But some ultramassive white dwarfs seem to be spinning near this limit, and yet holding themselves together. How? We're not entirely sure. It could be internal magnetic fields reinforcing the structure. It could be a weird fluid dynamic inside the star's degenerate matter. Whatever it is, it's another puzzle. There's also the puzzle of cooling. White dwarfs cool over time. That's well understood. But ultramassive white dwarfs might cool differently. They might crystallize sooner. That's right, crystallize. As they cool, their interiors might literally solidify, turning into a gigantic diamond-like structure made of carbon and oxygen nuclei arranged in a lattice. That's not poetic. That's real. Scientists think white dwarfs eventually become enormous cosmic diamonds. Now, take that idea and apply it to an ultramassive white dwarf. You're talking about something more massive than our Sun, made almost entirely of solid carbon, floating silently through space. That's one of the most bizarre and beautiful mental images in all of astronomy, a frozen sun-sized diamond drifting alone in the darkness of space. And if that wasn't strange enough, some researchers think that crystallization can release heat. That means as the white dwarf turns into a solid, it might actually warm slightly, for a brief period, before continuing its slow cooling. It's like a dying ember suddenly flaring up, just for a moment, because of the way its atoms are arranging themselves. It's the kind of thing that sounds like fantasy, but it's backed by real astrophysics. And it makes you think about how many of these quiet, dim stars in our sky might actually be ancient diamonds, slowly spinning, slowly fading, but still carrying secrets from the dawn of time. We haven't even scratched the surface yet. We haven't mapped their interiors. We haven't seen their depths. We haven't measured their magnetic skeletons, or listened to their seismic tremors. We haven't observed the moment they collapse into black holes, or the gravitational shutters they send across the universe. All of that is still to come. Ultramassive white dwarfs are the end result of something that started billions of years ago, long before humans walked the Earth. But they're also just the beginning of something we haven't fully discovered. And the more we learn, the more we realize how much we still don't understand. The mystery gets bigger. The questions get weirder. The stars get quieter. But the silence? The silence is louder than ever. They remind us that the universe is a place where the ordinary can become extraordinary. Where even death isn't the end. Where a dead star can still hold more mass than our entire Sunday. Where frozen light can shine with the echoes of ancient fire. Where something so quiet can be so powerful, so haunting, so full of stories we've only just begun to read. And somewhere out there, another one is waiting. Just a dim dot of light in a telescope image. But inside that dot could be a collapsed core, spinning faster than a bullet, heavier than anything nearby, colder than the void around it. Just sitting there. Watching. Waiting. Because the universe doesn't forget its secrets. It hides them in the bones of stars. And speaking of secrets, some ultramassive white dwarfs aren't just bizarre because of how heavy they are, but because of how they got that way. When you really think about it, a white dwarf that massive shouldn't even exist. Stars that big are supposed to skip the white dwarf phase entirely and go supernova, then become neutron stars or black holes. So how did these ultramassive white dwarfs slip through the cracks? It's like finding a person who's 8 feet tall and weighs 600 pounds, but still manages to be a ballet dancer. It doesn't add up, until you realize there's more going on than meets the eye. Astronomers now believe that many ultramassive white dwarfs are the result of stellar mergers. Imagine 2 regular white dwarfs, dead stars, already collapsed, no longer burning, locked in a binary orbit around each other. Over millions or billions of years, their orbits decay due to gravitational radiation. They spiral inward, closer and closer until, bam, they collide. Sometimes that creates a type I supernova. But sometimes, if the total mass doesn't quite reach the tipping point, they don't explode. They merge. And the result is a new, ultramassive white dwarf, one that was born not from the death of one star, but the fusion of 2. This is where things get even more interesting. These merger products can be unstable. Their cores might not be fully mixed. They can have chaotic internal structures, leftover magnetic fields from both parent stars, or even spinning cores surrounded by non-spinning outer shells. They can also show strange surface compositions, like unexpected traces of helium or metals in places they shouldn't be. These are like Frankenstein stars, stitched together from the remains of dead stars, lurching through space as a single massive body. And when we talk about magnetic fields, oh man, ultramassive white dwarfs are magnetic monsters. Some of the most magnetic objects in the universe aren't neutron stars, they're white dwarfs. And among them, the ultramassive ones tend to have the strongest fields. We're talking hundreds of millions of Gauss, enough to twist light and mess with atomic structures. Some even emit radiation from their magnetic poles, like pulsars do, though much fainter. These magnetic fields are so intense that they can sculpt the surface of the star, cause starquakes, and maybe even contribute to slowing down its spin over time. Now think about this. What happens if the magnetic field of an ultramassive white dwarf aligns just right with its spin? You get beams. Beams of radiation, like faint cosmic lighthouses. We've detected some of these, and they behave in ways that confuse astronomers. They're not quite pulsars, not quite normal stars. There's something in between. Something rare. Something strange. And if you're still wondering why this matters, why you should care about these frozen, dead stars, here's the thing. Ultramassive white dwarfs are future black holes. Many of them are probably just waiting for a little more mass to fall onto them, a bit more gas, a dust disk, maybe even a small planet. And the moment that pushes them over the Chandrasekhar limit, they collapse. Instantly. No warning. 1 minute they're there, the next minute they vanish, leaving behind only a gravitational echo. And what about planets? That's right, some ultramassive white dwarfs might have planets. Not normal ones, but weird ones. Survivors of the original star's death. Or leftovers from the merger process. These planets could be made of carbon. Or ice. Or metal. They might orbit very close, locked into decaying paths that slowly spiral inward, doomed to crash into the white dwarf and trigger its final collapse. We may have already seen signs of this: unusual emissions, sudden flashes, unexplained temperature spikes. All pointing to hidden companions in suicidal orbits. And we haven't even gotten to the wildest idea of all. Some astrophysicists have proposed that ultramassive white dwarfs could be linked to type Ia supernova imposters. These are events that look kind of like a supernova, but aren't caused by the usual mechanisms. Imagine a white dwarf that's teetering on the edge of collapse. It gains just a little bit of mass, enough to ignite carbon fusion in its core, but not enough to completely detonate. The result? A semi-explosion. A partial burn. The outer layers might be blown off, but the core remains. The star survives. Barely. Scarred. Altered. Different. But still there. That kind of event could explain some of the weird transient flashes we've seen in the night sky. Events that don't quite fit into any box. They're not novae, they're not full supernovae. There's something else. Something we don't yet understand. Something that might come from ultramassive white dwarfs on the edge. Now here's where it really gets mind-bending. If you look far enough back in time, billions of years, you'd find that white dwarfs were probably forming more frequently. The early universe was full of massive stars. Many of them lived fast and died young. And many of those deaths likely resulted in white dwarfs. So some of the ultramassive white dwarfs we're seeing today could be ancient. Older than Earth. Older than the solar system. Older than some of the galaxies we see. These stars are ancient fossils. And like fossils, they tell stories. Stories of the early universe. Of mergers. Of magnetic chaos. Of near-death collapses. Of survival against the odds. They are monuments to the extremes of stellar evolution. And they're still out there, still cooling, still spinning, still whispering secrets we haven't yet translated. And maybe, just maybe, they're not done yet. There's something almost poetic about how ultramassive white dwarfs defy both life and death. They're not quite alive in the way we think of stars. No nuclear fusion, no warm glow of hydrogen becoming helium. But they're not truly dead either. They're holding on, teetering between collapse and endurance, refusing to go quietly. It's like they've paused in the middle of their final breath, and just stayed there, suspended. And if we take a closer look at the physics going on inside these monsters, it becomes even more surreal. The matter in their cores isn't anything we experience here on Earth. It's degenerate. Not in the moral sense, of course, but in terms of quantum physics. In a normal object, like a rock or a planet, pressure comes from atoms pushing against each other. But in a white dwarf, the atoms have already been crushed. What's left is a sea of electrons, packed so tightly that they can't be pushed any closer together, not because of any physical barrier, but because of the Pauli exclusion principle. That quantum rule says no two electrons can occupy the same state at the same time. So in these ultramassive white dwarfs, the only thing holding the star up against its own gravity is that fundamental quantum rule. Literally, quantum mechanics is the scaffolding holding up the star. But here's the thing. That pressure, that quantum electron degeneracy pressure, it has a limit. And as the mass of the white dwarf increases, gravity gets stronger, and those electrons get squeezed harder. If you keep adding mass, eventually, the electrons can't take it anymore. They collapse into protons, forming neutrons. That's when you cross the Chandrasekhar limit, about 1.4 times the mass of the Sun, and the star becomes a neutron star. But ultramassive white dwarfs hover dangerously close to that line. They're like tightrope walkers, balancing on the edge. One false move, a planet crashes in, or a nearby star donates some matter, and the game is over. Now here's a question scientists have started asking. Could some ultramassive white dwarfs be hiding their true mass? Think about it. If a white dwarf has a strong enough magnetic field, it might be distorting the way light leaves its surface. It could be spinning so fast that its shape is stretched into an oblate spheroid, wider at the equator than at the poles. These distortions can trick our instruments. What if the true mass of some white dwarfs is actually higher than what we've calculated? What if we've already discovered white dwarfs that are past the Chandrasekhar limit, and we just haven't realized it? That opens up a weird possibility: stable objects beyond the known limit. Are they being stabilized by something exotic? Dark matter, perhaps? Or unknown forms of quantum pressure? These are huge questions, questions that could rewrite our understanding of stellar death and structure. And here's another bizarre twist. What if some ultramassive white dwarfs never actually formed through regular stellar evolution? What if they were born that way, under extreme early universe conditions? We know the early universe had different chemical compositions, more hydrogen and helium, less of everything else. Maybe, under the right circumstances, an early star could collapse directly into an ultramassive white dwarf without ever passing through the usual red giant or supernova phases. These would be true relics, cosmic time capsules from a time when galaxies were just starting to form. Now imagine this: you're looking through a telescope, observing a faint, cold object in the distance. It doesn't emit much light, just a dim glow in the infrared. But its gravity is strong, way too strong for something its size. Its magnetic field disrupts background radiation. It barely spins, and its surface is cool to the touch, just a few thousand degrees Kelvin. You might be looking at an ultramassive white dwarf that's been drifting through space for 10 billion years. A ghost. A fossil. A puzzle. And if that sounds creepy, here's the kicker: we might be surrounded by them. The Milky Way could be full of ultramassive white dwarfs we haven't detected yet. They don't give off strong light. They don't have huge magnetic flares. They're just there. Waiting. Hiding in the dark. Waiting for some event, maybe a merger, maybe a planetary impact, to push them over the edge. Now here's a concept that could blow your mind: crystallization. As white dwarfs cool down, they solidify. Literally. They turn into giant crystals made mostly of carbon and oxygen. It's been observed, and it's not science fiction. The larger and older the white dwarf, the more likely it is to be crystallized. So, some ultramassive white dwarfs out there are basically planet-sized diamonds floating through space. That's not poetic, it's literal. A diamond the size of the moon. Or even bigger. But crystallization isn't just beautiful, it changes the game. When a white dwarf crystallizes, it releases latent heat, which slows down the cooling process. That makes the star shine a little longer than expected. It also shifts the star's internal structure, which could influence how it collapses later. Some scientists think crystallization could delay the collapse into a neutron star or even trigger unique types of stellar quakes, massive seismic events that shake the entire dead star. And here's something even more wild: what if life once orbited one of these ultramassive white dwarfs? Think about the parent star. Long ago, before it died, it may have had planets. Maybe even habitable ones. When it went red giant, it would have scorched everything nearby. Then, as it collapsed into a white dwarf, any surviving planets might have been flung outward, or inward. Some might have remained caught in strange new orbits around this now dead star. And who knows? Maybe microbial life survived on one of those distant moons. Maybe it's still out there. This gets even more mind-blowing when you consider the time scales involved. White dwarfs cool slowly. They can shine faintly for tens of billions of years. That means ultramassive white dwarfs could outlive most stars in the universe. Long after the sun dies, long after the galaxies fade, these ancient remnants might still be glowing faintly in the darkness. Some physicists have even speculated that white dwarfs could be among the last visible objects in the far future of the universe. Imagine that, trillions of years from now, in a universe gone cold and empty, ultramassive white dwarfs might still be sitting there. Cold. Dense. Silent. But still existing. And all that from the remains of a star. Now, if you're wondering how we actually detect ultramassive white dwarfs out there in the vastness of space, the answer is both fascinating and challenging. Unlike bright stars that shine with intense light, white dwarfs are faint and often require very sensitive instruments to find. Astronomers often look for these objects using specialized telescopes that can detect light outside the visible range, like ultraviolet or X-rays, because the surface temperatures of young white dwarfs are extremely high, making them glow strongly in those ranges. But as white dwarfs age and cool, they fade, making it much harder to spot the ultramassive ones, especially because they're rarer and often cooler. One of the primary techniques scientists use involves measuring the star's mass and radius. The two are linked by the mass-radius relationship, a unique property of white dwarfs where the more massive a white dwarf is, the smaller its size. That's the opposite of what happens in normal objects like planets or stars. This relationship is governed by the physics of electron degeneracy pressure mentioned earlier. By measuring how big a white dwarf appears in the sky, its radius, and how bright it is, which tells us temperature and luminosity, astronomers can estimate its mass. If the mass comes out very close to or above the Chandrasekhar limit, then they suspect an ultramassive white dwarf. Sometimes, ultramassive white dwarfs reveal themselves through their effect on nearby objects. For instance, if the white dwarf is in a binary system with a companion star, it might pull matter from that companion. This accretion of matter can cause the white dwarf to heat up and emit X-rays, making it easier to detect. Observing such systems has provided some of the best candidates for ultramassive white dwarfs. But the story doesn't end there. Many ultramassive white dwarfs are believed to have incredibly strong magnetic fields, millions to billions of times stronger than Earth's magnetic field. These magnetic fields can create complex and sometimes strange surface patterns. The fields can also affect how the star cools and how it interacts with its surroundings. Some astronomers think these strong magnetic fields are a clue to how these stars formed and evolved. Perhaps when two smaller white dwarfs merge, the intense compression and twisting of matter generates a massive magnetic field. Or maybe the magnetic fields are leftovers from the progenitor star. Speaking of mergers, one of the most dramatic paths to creating an ultramassive white dwarf is through the merging of two smaller white dwarfs. Imagine two dead stars locked in a tight orbit, spiraling closer and closer due to gravitational wave radiation, the very ripples in spacetime that physicists detected in 2015. Eventually, these two stars collide, merging into a bigger, heavier white dwarf. This process can push the combined mass dangerously close to the Chandrasekhar limit. Depending on how massive the merged star is and how fast it cools or spins, it might remain stable as an ultramassive white dwarf for millions or billions of years, or it might collapse into a neutron star or explode as a Type Ia supernova. Type Ia supernovae are some of the most important cosmic events for astronomers because they serve as standard candles to measure distances in the universe. However, understanding exactly how these explosions occur is complicated. Ultramassive white dwarfs could play a key role in this puzzle, especially the ones that form from mergers. If a white dwarf crosses the Chandrasekhar limit by gaining too much mass, it can no longer support itself, and it undergoes a runaway fusion reaction, blowing itself apart in a brilliant supernova. But if the star's rotation or magnetic field temporarily supports it, it might delay or change the nature of the explosion, leading to subtle differences in brightness or spectral signatures. Another fascinating mystery about ultramassive white dwarfs is their composition. While many typical white dwarfs are made mostly of carbon and oxygen, the ultramassive ones might contain heavier elements like neon and magnesium. This is because the progenitor stars that formed them were much more massive and went through more complex fusion reactions before collapsing. These heavier elements could change how the star behaves during crystallization and cooling, and might also affect the star's ability to collapse or explode. It's also important to consider the role of rotation. Some ultramassive white dwarfs spin incredibly fast, many times per minute, while others rotate more slowly. Rapid rotation can provide extra support against gravitational collapse by creating a centrifugal force pushing outward. But spinning too fast can also cause the star to wobble or lose stability, potentially triggering mass loss or an explosion. The balance between spin, magnetic fields, mass, and temperature creates a rich and complicated story of stellar life and death. When we zoom out to the bigger picture, ultramassive white dwarfs can tell us a lot about the history of the universe. By studying their distribution in the galaxy, where they're located, how many there are, how old they are, astronomers can piece together clues about how stars have evolved over billions of years. For example, these stars might help us understand star formation rates in the early Milky Way or reveal hidden populations of ancient stars that survived the violent phases of galaxy evolution. There's even the possibility that ultramassive white dwarfs are related to some of the most mysterious signals detected by astronomers. For example, fast radio bursts, FRBs, brief, intense bursts of radio waves from unknown cosmic sources, might be connected to white dwarfs with extreme magnetic fields or unusual internal structures. Some theories suggest that interactions in binary systems involving ultramassive white dwarfs could create conditions for these bursts. While it's still speculation, the connection is an exciting area of research. Then there's the question of what the future holds for these stars. Some might quietly cool and fade away over trillions of years, becoming what's called black dwarfs, hypothetical dark stellar remnants that no longer emit light. Others might end their lives in spectacular explosions or collapse into neutron stars or even black holes. The fate of an ultramassive white dwarf depends on so many factors: mass, spin, magnetic fields, interactions with companions, that predicting their future is a huge challenge. What makes this even more fascinating is that ultramassive white dwarfs challenge our understanding of physics in extreme conditions. They are natural laboratories for studying matter at densities and pressures impossible to recreate on Earth. Each discovery about them can influence our knowledge of quantum mechanics, nuclear physics, and even general relativity. We can't forget the human side of this story. It's the curiosity and determination of scientists using the latest telescopes and simulations that bring these distant, mysterious objects into the light. Every new ultramassive white dwarf discovered is a step closer to answering some of the universe's biggest questions. How do stars live and die? What happens to matter at extreme densities? And what secrets lie hidden in the dark, cold corners of space? Ultimately, ultramassive white dwarfs are like cosmic puzzles, pieces of a vast, complex picture of the universe's life cycle. They're remnants of stars that once shone brightly but now exist in a delicate balance between existence and oblivion. Understanding them helps us understand ourselves and the universe around us, revealing the incredible forces shaping everything from the tiniest atom to the largest galaxies. Their story is still being written, and with every new observation, theory, and discovery, we move closer to unveiling the true nature of these ultramassive stellar ghosts. And who knows? Maybe one day these dense, silent stars will hold the key to unlocking the ultimate mysteries of space, time, and matter. Ultramassive white dwarfs don't just stand alone in space quietly fading away. Some of them are part of complex systems with other stars or even exotic objects like neutron stars and black holes. In these systems, the dynamics can become incredibly intense. Picture two dead stars locked in a tight gravitational dance. The interaction can lead to mass transfer, where one star steals gas from the other, changing both their fates dramatically. This process can affect the ultramassive white dwarf's stability, and even push it closer to exploding as a supernova. One particularly intriguing question scientists ask is how ultramassive white dwarfs influence gravitational waves. Gravitational waves are ripples in the fabric of space-time caused by massive objects accelerating, like black holes or neutron stars merging. While white dwarfs are less massive than black holes or neutron stars, when two white dwarfs in a binary system spiral inward and merge, they could create gravitational waves detectable by instruments like LISA, the future space-based Gravitational Wave Observatory. Detecting such signals could reveal how often ultramassive white dwarfs form from mergers and help confirm theories about their birth. Another fascinating aspect of ultramassive white dwarfs is their crystallization process. Unlike the Earth's solid crust, white dwarfs crystallize from the inside out. As the star cools, its interior begins to freeze into a solid lattice of ions. For typical white dwarfs, this process is slow and subtle, but for ultramassive white dwarfs, crystallization happens much earlier because of their higher densities and pressures. This phase change affects the star's heat flow, brightness, and cooling rate, and can even produce seismic vibrations detectable as tiny changes in brightness, known as stellar pulsations. Studying these pulsations allows scientists to probe the star's interior, a method called astroseismology. The idea that ultramassive white dwarfs might contain exotic particles or states of matter is a thrilling frontier. Some researchers speculate that under the extreme densities inside these stars, electrons might combine with protons to form neutrons, or strange quark matter might appear, a state even denser than neutron stars. These exotic possibilities could make ultramassive white dwarfs a transitional stage between normal white dwarfs and neutron stars, blurring the lines between different types of stellar remnants. On a broader scale, ultramassive white dwarfs play a role in the chemical evolution of galaxies. When some of these stars explode as supernovae, they scatter heavy elements like iron, nickel, and others into space. These elements eventually become part of new stars, planets, and even life. Without these explosions, the universe would lack many of the elements essential for forming rocky planets like Earth. So, ultramassive white dwarfs help recycle matter and build the cosmic environment that supports life. Astronomers are constantly hunting for more ultramassive white dwarfs using surveys like Gaia, which measures the positions, distances, and motions of stars with unprecedented precision. Gaia's data has revolutionized our understanding of the Milky Way's structure and stellar populations. From this treasure trove, astronomers have identified candidates that might be ultramassive white dwarfs based on their unusual brightness, temperature, and movement. Each discovery adds another piece to the cosmic puzzle. Looking ahead, new telescopes and instruments coming online will deepen our understanding of these enigmatic stars. For example, the James Webb Space Telescope, operating in the infrared, can detect cooler, older ultramassive white dwarfs that were previously invisible. Meanwhile, planned X-ray and gravitational wave observatories will open new windows into the behavior of these stars in extreme environments and during explosive events. The mysteries surrounding ultramassive white dwarfs also touch on fundamental physics. These stars push the limits of quantum mechanics and relativity, forcing physicists to refine their models of how matter behaves under extreme conditions. Each discovery challenges our understanding and sometimes even reveals gaps in the theories we thought were solid. This constant back and forth between observation and theory is what drives science forward. Even the environments around ultramassive white dwarfs can be surprising. Some may host disks of gas or debris left over from past interactions or mergers. These disks might feed the star or produce jets of particles and radiation. Observing such phenomena can tell us about the history and evolution of the system, as well as test our understanding of astrophysical processes in dense environments. The fact that these stars can survive mergers without immediately collapsing or exploding also raises questions about the internal physics that govern their stability. How does matter resist collapse at these extreme densities? How do magnetic fields and rotation change the picture? Exploring these questions helps scientists build better models of stellar structure and evolution. For the everyday person, understanding ultramassive white dwarfs might seem like a distant cosmic curiosity. But these stars are more than just astronomical oddities. They connect directly to the origins of the elements that make up our world and the universe's grand story. They are the endpoints of some of the most massive stars, and their lives and deaths influence the galaxies we see today. Ultramassive white dwarfs challenge what we thought we knew about star life cycles. Once, it seemed clear that stars below a certain mass became white dwarfs, and those above another threshold became neutron stars or black holes. But these stars show that reality is messier and more complex. Sometimes, nature creates borderline cases that force us to rethink categories and definitions. In fact, as technology improves, we might find even more extreme examples of white dwarfs, pushing the boundaries of mass and density even further. Some scientists speculate about Superchandrasekhar, white dwarfs, stars that somehow support more mass than the traditional limit, perhaps through rapid rotation or strong magnetic fields. Finding such stars would revolutionize our understanding of stellar physics. Meanwhile, the search for ultramassive white dwarfs also ties into the hunt for dark matter. Some theories propose that these stars could capture dark matter particles, which might influence their cooling and internal structure. Studying deviations in cooling rates or unexpected properties could provide indirect clues about the nature of dark matter, one of the biggest mysteries in physics. The intersection of ultramassive white dwarfs with other cosmic phenomena doesn't end with gravitational waves or supernovae. Some scientists are investigating whether these stars could be linked to certain types of gamma-ray bursts or unusual X-ray sources. By piecing together clues from multiple wavelengths and cosmic messengers, we can start to see a bigger picture of how these objects fit into the energetic universe. At the same time, ultramassive white dwarfs remind us how much we have yet to learn about the universe. Despite decades of study, the complexity and variety of these stars continue to surprise. Every new discovery, whether it's a strange magnetic field, an unexpected mass measurement, or an unusual cooling behavior, opens new questions and mysteries. One of the remarkable aspects is how interconnected astrophysics is. To understand ultramassive white dwarfs, scientists use knowledge from nuclear physics, quantum mechanics, thermodynamics, general relativity, and even particle physics. These stars act as cosmic crossroads where multiple branches of physics intersect, making them invaluable for research. And it's not just professional scientists who can be fascinated by these stars. Ultramassive white dwarfs inspire wonder and curiosity about the cosmos. They remind us of the incredible extremes nature can reach and the limits of human knowledge. They are stars that have lived fast and died spectacularly, now quietly holding secrets of the universe's deepest laws. Ultramassive white dwarfs are among the most mysterious and intriguing objects in space. Their unusual masses, intense densities, strong magnetic fields, and complex evolution set them apart from their smaller white dwarf cousins. They are crucial for understanding the life cycles of stars, the origins of heavy elements, and the dynamics of extreme astrophysical systems. As our tools improve and new observations pour in, the story of ultramassive white dwarfs will continue to unfold. They will likely keep surprising us with new behaviors and properties, challenging existing theories and inspiring new ones. Through studying these dense, ancient stars, we gain insight not only into the universe's past but also its future. No matter how deep we dig into space or how far our telescopes reach, ultramassive white dwarfs stand as a reminder. The universe is stranger and more complex than we can imagine, filled with wonders waiting to be discovered. The journey into understanding ultramassive white dwarfs is also a journey into the unknown boundaries of physics. These stars force us to ask questions that bridge the gap between astronomy and the fundamental laws governing matter and energy. For instance, how exactly does matter behave when packed so densely that atoms themselves are crushed? In these stars, electrons are squeezed into an incredibly tight space, and the resulting pressure is what keeps the star from collapsing. But the details of this quantum pressure, known as electron degeneracy pressure, become more complicated as density increases, and ultramassive white dwarfs push these limits. Scientists use complex computer models to simulate what happens inside these dense stellar remnants. These simulations must incorporate quantum mechanics, thermodynamics, and relativity to predict the star's structure, temperature distribution, and evolution over time. The models can show how ultramassive white dwarfs cool, how they crystallize, and what might trigger their collapse or explosion. Comparing these predictions with observations helps refine our understanding, but challenges remain, especially for stars at or above the Chandrasekhar mass limit. Magnetic fields in ultramassive white dwarfs add another layer of complexity. Some of these stars exhibit magnetic fields billions of times stronger than Earth's. Such fields influence the star's shape, possibly making it less spherical and more elongated. The magnetic pressure can support additional mass beyond what electron degeneracy alone can hold, offering a possible explanation for some ultramassive white dwarfs exceeding the Chandrasekhar limit. Magnetic fields can also channel matter in binary systems, affect stellar winds, and play a role in the star's cooling and crystallization processes. Rotation is yet another factor that changes the game. Many ultramassive white dwarfs spin rapidly, sometimes several times per minute. This rapid spin provides centrifugal force, which counteracts gravitational collapse, enabling the star to support more mass temporarily. Over time, as the star loses energy through radiation and magnetic braking, the spin slows, potentially pushing the star closer to instability. Understanding how rotation and magnetic fields combine to affect these stars is an active research area, and it could reveal pathways to unusual supernovae or other explosive events. Ultramassive white dwarfs are closely linked to the phenomenon of Type Ia supernovae, some of the universe's most powerful and important explosions. These supernovae serve as standard candles in cosmology, helping measure the expansion rate of the universe. The classic model involves a white dwarf in a binary system accumulating mass from its companion until it reaches a critical limit and detonates. However, ultramassive white dwarfs challenge this view. Their unique properties might explain why some Type Ia supernovae appear brighter or dimmer than expected, indicating variations in the progenitor stars. This possibility has major implications. If ultramassive white dwarfs cause some of these supernovae, it means the universe's expansion rate estimates might need adjustment. Since dark energy studies depend heavily on type I supernovae data, understanding ultramassive white dwarfs is crucial for cosmology itself. It's a prime example of how studying these dense stellar remnants can ripple out into broader scientific questions about the fate and structure of the entire cosmos. Discoveries of ultramassive white dwarfs also come with surprises about their atmospheres. Unlike younger, less massive white dwarfs with hydrogen or helium atmospheres, some ultramassive white dwarfs show unusual chemical signatures. Elements heavier than helium, called metals, in astronomy, sometimes appear in their atmospheres. Since heavier elements should sink quickly under gravity, their presence hints at recent accretion events or ongoing processes replenishing these elements. This could involve material captured from interstellar gas, disrupted planetary bodies, or leftover debris disks. The possibility of planets orbiting or orbiting remnants around ultramassive white dwarfs is another captivating idea. Although the violent history of the progenitor star would likely destroy or strip any original planetary system, new planets might form from debris after the star's death. Alternatively, rogue planets could be captured into orbit. Detecting planets around ultramassive white dwarfs would be incredibly challenging but could reveal how planetary systems survive or evolve around dead stars. Astroseismology, the study of starquakes and pulsations, offers a rare window into the interiors of these stars. Ultramassive white dwarfs can pulsate in specific modes that depend on their internal structure, composition, and temperature. By observing the frequencies and patterns of these pulsations, astronomers decode the star's inner layers much like seismologists study Earth's interior from earthquakes. These measurements refine models of ultramassive white dwarfs' cores, crystallization fronts, and envelope structures, unlocking secrets about matter under extreme conditions. Another exciting area concerns how ultramassive white dwarfs relate to the formation of neutron stars and black holes. The traditional idea is a clean line: stars below a certain mass become white dwarfs, those above become neutron stars or black holes. However, ultramassive white dwarfs may be the middle ground or a transitional phase. If pushed beyond stability, they might collapse directly into neutron stars without a supernova explosion, or create exotic phenomena like electron capture supernovae. Understanding these pathways helps explain the population and distribution of compact objects in the galaxy. The origin of ultramassive white dwarfs remains partly mysterious. Some form from single stars with very high initial masses, but many are thought to result from the merger of two less massive white dwarfs in binary systems. When two white dwarfs spiral together due to gravitational wave emission, they can collide and merge into a heavier ultramassive white dwarf. The conditions of these mergers, mass ratios, spin, magnetic fields, determine the fate of the new star, whether it remains stable, explodes, or collapses. This merger process is not just a theory. Observations of certain white dwarf binaries, combined with gravitational wave studies, support this idea. Future space observatories designed to detect low-frequency gravitational waves may directly observe these mergers, offering a new way to study ultramassive white dwarfs in formation and their explosive ends. This would be a breakthrough in understanding how such exotic objects are created. The extreme densities inside ultramassive white dwarfs also raise questions about the possible existence of strange states of matter. Some physicists propose that under such intense pressure, matter could transition into forms made of strange quarks or other exotic particles. If true, ultramassive white dwarfs could become natural laboratories for testing particle physics theories beyond what we can recreate on Earth. This link between the largest scales of the universe and the tiniest particles is one of the most fascinating aspects of astrophysics. Looking even further, ultramassive white dwarfs might play a role in the broader cosmic ecosystem. Their formation and eventual explosions enrich galaxies with heavy elements needed for new stars, planets, and life itself. Their explosions can trigger star formation by compressing nearby gas clouds. In this way, they participate in a cycle of cosmic birth and death, connecting the past and future of the universe. The study of ultramassive white dwarfs also has practical implications for space exploration and understanding the Milky Way. By mapping their locations, astronomers can trace the history of star formation in our galaxy. These stars are remnants of earlier generations of massive stars, so their distribution offers clues about where and when those stars lived and died. This contributes to our knowledge of the galaxy's structure, evolution, and the processes shaping its current state. Despite their importance, ultramassive white dwarfs remain difficult to observe. Their compact size, faint light, and rarity make them elusive targets. However, advancements in telescope technology, data analysis methods, and international collaborations are rapidly expanding our ability to detect and study these objects. Large sky surveys, combined with specialized instruments, are increasing the known population and uncovering new phenomena associated with these dense stars. As research continues, ultramassive white dwarfs will likely continue to surprise scientists and enthusiasts alike. Their unique combination of extreme physics, connection to cosmic evolution, and role in explosive phenomena ensures they remain a hot topic in astrophysics. Each new discovery not only enriches our understanding of these stars but also deepens the mystery, driving curiosity and scientific inquiry. In the grand scheme, ultramassive white dwarfs serve as a reminder that the universe is filled with extremes beyond everyday experience. They show us how matter can behave in ways that challenge intuition and extend the limits of known physics. They invite us to look up and wonder about the forces shaping the cosmos and our place within it. To sum it up, ultramassive white dwarfs are dense, fascinating objects sitting on the edge between different types of stellar remnants. They offer insight into stellar death, the creation of heavy elements, the origins of supernovae, and the physics of matter under unimaginable pressure. Their study involves a complex interplay of observation, theory, and advanced technology, connecting many fields of science. These stars hold keys to understanding the life cycle of matter and energy in the universe. They are a vital piece in the cosmic puzzle, linking stellar evolution to galactic chemical enrichment, and even cosmology. As our tools and knowledge grow, ultramassive white dwarfs will continue to illuminate the mysteries of the cosmos in ways we can hardly predict. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.